Hello.
Hello, Josh.
Hey,
Hi. How are you?
pretty good. How are you?
Good, good.
I got very confused by the like difference of 30 minutes in our time zones. I
Oh,
was all
right.
ready to go 30 minutes ago, and
I
then I
get
realized
confused
I
all
was
the time.
off.
Right. So, which part of the US are you currently on the East Coast?
Yeah,
Or
I'm on
the
the East Coast. Yeah, I'm near Boston still.
Yeah. Okay.
Pretty good. How are you?
Oh, yeah. My YouTube stream was on, so I was in the
Oh,
same.
I see. All right. I want to test to make sure my slides work correctly.
Sure. Can you
Yeah.
start sharing? You are giving the first talk, right?
Yeah. I hope so.
Yeah. I mean, even I checked.
Okay.
Wendy is giving the second talk, and
This. Share. All right. Can you see my slide?
yes. Can you flip like next to the next slide?
Yeah.
Yes. Okay, I can see the
Oh, okay. I want to test also. Can you see? Oh, is this working?
Pencil.
Oh, my PowerPoint restarted itself.
Wow.
I hope that's not going to be an issue. Okay. Well, okay. Let me double check. Nothing bad just happened. Okay, that should be fine. That should be fine. Okay, let me try again. Okay, I'm going to share screen again. Maybe I just want to do this. Share. Okay, can you see the slide now?
Yes, the first slide now. Yes, I can see the first slide.
Okay,
second
and now
slide.
you can see the second slide. Okay,
yes.
And let me try this again. And can you see that I'm writing something? Hello?
Yes, writing hi. Sorry, I
All
was
right.
joking, yeah.
Okay, excellent. And
yes, I can see everything.
Okay, I think I'm all set then.
So I made you and Bentley a co-host. So if my internet connection drops off, for a minute or maybe for a second, then one of you will become a host. But then if that happens, then just give me my host privileges back, so that I can other people.
Okay, sounds good.
So what is Gather Town about?
So in Gather Town, you can click on the link. And you can see people there.
So is there a
Right?
specific time?
You see people roaming around. You can go to anyone and then start talking.
Okay, is there a specific time for that, or
It's happening in between the talks as well as after the workshop.
okay?
Yeah, so it should be live between the breaks.
Hi, May. Hi, Josh.
Oh, hello.
Hello.
Hi, Satya.
Good morning. Or good evening, I guess.
Yeah, good evening. Yeah, I'm very grateful that I'm giving the first talk of the session, because otherwise I might fall asleep during my talk.
Right. Yeah. Well, it's interesting times. Well, I don't know. It's nothing to be laughed about, but yeah, it's hopefully it won't last long. But on the positive side, this makes it easy to organize conferences that everybody can attend.
Yeah,
Right.
for sure.
Yeah, yeah, it turns out that I'm able to go to more conferences and workshops this year because of virtual events than when they happen physically. Because when they are physical conferences, you have no choice. I mean, most of the time you don't have any choice. Whereas now you do have a choice. So I think going forward we will have a choice of attending in person versus attending virtually, which makes it actually a good thing for people who have to travel across the world.
Yeah. Yeah, I agree. Yeah, I'm excited to see what format conferences will take after it's safe to travel again. Like what kind of hybrid setup people will come up with.
Right. Yeah. Yeah. So we're almost on the hour, but we'll give a couple of minutes, Josh, if that's okay with you.
Yeah, yeah.
Sure.
So, Josh, is it okay for people to interrupt you during the talk, or do you want to take all the questions at the end?
Yeah, yeah. Please interrupt me during the
Okay,
talk.
good. Yeah. That's better. Given that these are hour-long talks, I think it's okay.
Yeah, I agree.
Yep.
And if someone sends messages to the Zoom chat, I might miss it. So
No, I will watch out for it. Yep.
Okay, great.
That's fine.
Yeah, I will also be monitoring the chat box.
Okay, thanks.
So I guess, people might walk in slowly, but can we start, Josh?
Yeah. I'm all set.
Okay. All right, everyone. Welcome to the second day of this workshop on matrix rigidity. And today we have three exciting talks lined up. First up is Josh Ullman. Josh is currently a Rabin postdoc in theoretical computer science at Harvard University. Before this, he received his PhD from MIT with Ryan Williams and Virginia Williams as his advisors. Josh is interested in design of algorithms and complexity theory, in particular using algebraic techniques to solve problems all over computer science. In fact, with Virginia Williams, he contributed the best known bound on the matrix multiplication exponent. With Ryan Williams and Li-Ji Chen, he has obtained several surprising results on matrix rigidity, and some of them we will see here, hopefully. And in fact, Josh won 2 Best Student Paper Awards, one in Fox 2019 with Li-Ji Chen, and another at CCC 2019. Today, he's going to tell us about recent results on matrix rigidity upper bounds. Josh, go ahead.
Thanks. Thank you for the introduction, Satya, and thanks for the organizers for putting this together and inviting me. Yeah, so I'm going to talk about matrix rigidity upper bounds today, and the organizers, I guess, were very clear that the other talks in the workshop are about rigidity lower bounds, and so I really have to talk about rigidity upper bounds. And so if you catch me, talking about lower bounds for too long, please interrupt me, and I'll try to get back on course. All right. So, okay, so here we go. So I guess yesterday we saw 2 nice tutorials about like introduction to matrix rigidity already. So I won't spend too long like introducing the background, but I do want to remind you of the main notions that we're going to be using in my talk. So we say a matrix M is rigid if it's far away from any low rank matrix. And by far away, we mean in Hamming distance. So you have to change lots of its entries to make it low rank. And more specifically, we write it like this. The rank R rigidity of M, denoted like R sub M for the matrix, and in parentheses R is the rank, is the minimum number of entries that you have to change in M to make its rank at most R. So just to give 2 examples, if you look at the n by n identity matrix, then for any rank R, its rank R rigidity is n minus R, because if you just change n minus R of the ones along the diagonal to 0, then it becomes a rank R matrix. So this is the identity matrix is actually the least rigid matrix among all full rank matrices, because you can keep just changing 1 entry to decrease its rank by 1. So in contrast, if you look at a random n by n matrix, let's say over F2, then it's very rigid with high probability. So for instance, with high probability, if you look at any sublinear rank, so if it's an n by n matrix, you look at any rank R that's small o of n, then with high probability, its rigidity for rank R is omega of n squared. So you have to change like a constant fraction of the entries of the matrix to drop its rank to R. Okay, so this is just the definition again. So rigidity was introduced by Les Valiant in the 70s to study arithmetic circuits. So what he showed is that for every n by n matrix that's computable by a linear size log depth arithmetic circuit, it has this rigidity upper bound. So for any epsilon, you can change just n to the 1 plus epsilon entries of the matrix to drop its rank to a little bit sublinear, like n over log n. So we don't currently know how to show that there are any like explicit functions that can't be computed by a linear size log depth circuit. So a big challenge is to construct matrices that don't have such a rigidity upper bound. So in other words, a rigidity lower bound that's stronger than this. So I mentioned on the last slide, a random matrix is rigid with high probability. But in the context of these circuit lower bounds, that's not super exciting, because like we already know that's how to show that a random function can't be computed by small circuits with high probability. So the real challenge is to show that there's an explicit family of matrices, like Fourier matrices or van der Waals matrices or Hadamard matrices or something that's rigid. And in this talk, what I'm going to talk about is, in some sense, the exact opposite of that. So I'm going to talk about how to show a matrix is not rigid. So you might ask, Josh, why would, if the goal is to show that there's rigid matrices, why are you going to talk for a whole hour about showing matrices are not rigid? So I think there's at least a couple of really good reasons to study this. First of all, like as in any area of trying to prove lower bounds, it's generally important to understand how the upper bounds work and what types of upper bounds you can hope to prove. So as we're going to see today, there are actually a lot of matrices that were previously conjectured to be rigid, and we're actually going to be able to prove in this talk that they're not rigid. So it's a good way to rule out non-rigid matrices and focus our attention on ones that might actually be rigid to prove. But there's also, so like low rank plus sparse matrix decompositions arise really naturally in a lot of algorithmic applications as well. So there's actually interesting applications just of the rigidity upper bound itself. And depending on how much time I have, I might talk a little bit about this at the end of the talk. Okay, well, let's get into it. So I wanna show for you in today's talk 2 techniques for proving rigidity upper bounds. So the first one is a technique I'll call diagonalization, where the idea is that if you show that a matrix A is not rigid, then that implies that for any diagonal matrix D, the matrix A times D times A is not rigid. So in other words, if you show that A is rigid, then any matrix that A diagonalizes is also not rigid. So that's the first technique we'll look at, diagonalization. I'll talk a lot more about it in a second. And the second technique I'll talk about is called the polynomial method, where the idea is that if a low degree polynomial computes most of the entries of a matrix A, then that means that matrix A is not rigid. So if there's a polynomial that takes in as input like a row index and a column index, and it outputs the matrix entry most of the time, and that polynomial is low degree, then that will mean that the matrix A is not rigid. So those are the 2 techniques we're going to look at. And what are we going to prove using them? So the first result I'll talk about is a joint result with Ryan Williams, where we showed that the Walsh-Hadamard transform is not rigid. And actually, I'm going to show a new generalization of that result of ours. So even if you've seen our proof before, you still won't have seen the proof I'm about to give today. So hopefully it will still be exciting to you. And then the second result I'll present is a result of Zev Devere and Ben Edelman, who studied these matrices of this form that I won't say too much about it right now, but I'll talk more about it later. So I'm gonna present these 2 proofs actually in all the details, and you'll see it's once you have the right idea of what to do, the proofs are not too complicated. It'll just be some linear algebra and some simple combinatorics. So that's the main plan. At the end, I'll talk a little bit about some follow-up work by Zev Devere and Alan Liu, who generalized these results to show that even more matrices are not rigid, like Fourier circulant group algebra matrices. So these are the results I'm going to talk about today. And before we get into it, I do want to mention that this talk is not intended to be like a comprehensive list of all known rigidity upper bounds. So there's plenty of results and techniques that I'm not going to talk about. Actually, Sasha in his talk yesterday listed a lot of them, so I'd recommend watching that if you want a reminder. But I'm mostly going to focus on these techniques that have been used in a few of these recent results. Okay, so let's get started, if there are no questions, with technique 1. Okay, so diagonalization. If A is not rigid, then for any diagonal matrix D, the matrix A times D times A is not rigid. So I'll get to this in a second, but I first am going to do a little bit of a bait and switch on you. And actually, for the rest of the talk, instead of talking about rigidity, I'm going to talk about a slight weakening of rigidity that I'll call row column rigidity. That's defined in this way. So it's like the notation's the same as rigidity, but there's this RC here to tell you it's the row column version of rigidity. So it's just the row column rigidity of matrix M for rank R is the minimum number of S so that you can change at most S entries in each row and each column of the matrix M to make its rank at most R. So this is weaker than rigidity in the sense that if you prove, well, if you prove a row column rigidity upper bound, that implies a regular rigidity upper bound as well, just like the row column rigidity times the side length of the matrix gives an upper bound on the rigidity. The other directions is not clear in general. It could be that like the best rigidity upper bound involves like packing many of the non-zero entries into just a few of the rows and columns. So maybe you wouldn't get a good row column upper bound. But so in this talk, I'm actually going to just give row column rigidity upper bounds, which imply regular rigidity upper bounds. So for our purpose today of just proving rigidity upper bounds, it'll be fine. And in fact, even our results will be even a bit stronger by focusing on this notion instead. Although if you wanted to prove lower bounds, then lower bounds on this notion are not necessarily sufficient to prove the applications you'd want. Okay, so just to give one example, so for the identity, the n by n identity matrix again, actually its row column rigidity for rank 0 is just 1, because if you change all of the ones on the diagonal to 0, then that makes the rank 0, gets the all zeros matrix. And in each row and each column, you've only changed one entry. Okay, so let me prove the first lemma about these things, which is that if A and B are matrices whose row column rigidity is low, so for each of them, their rank R row column rigidity is at most S, then that means the row column rigidity of their product is also not too big. So if for both of them, you can change S entries in each row and column to make the rank at most R, then that means in the product, you can change at most S squared entries in each row and column to make the rank at most 2R. That's what I'm going to prove. Okay, so first of all, well, since A and B are not rigid, we can write out their non-rigidity expressions. So we can write A as LA plus SA and B as LB plus SB, where LA and LB are low rank matrices. They have rank at most R. And SA and SB are sparse matrices. They each have at most S non-zero entries in each row and column. And then the key idea in this proof is the following. So if you take the product of just those sparse parts, the product of SA times SP, then the result is also somewhat sparse. It has at most S squared non-zero entries in each row and column. So let me like draw a picture of why that is. It kind of just follows from the definition of matrix multiplication. So if you have SA times SB is SA times SB. And then let's look at, let's say, a particular row of the product and ask how many ones or how many non-zero entries can be in this row. Well, what's the definition of this row? Well, we look at the corresponding row in the matrix SA. We know this row has at most S non-zero entries in it by definition over here. So then we look at the corresponding at most S rows of SB. They'll look like this. There they are. And our final like output row of SA times SB is some linear combination of these S rows of SB. Okay, and each of those rows of SB, once again, has at most S non-zero entries in it. And so when you add together S vectors, each of which has at most S non-zero entries, you'll get at most S squared non-zero entries. So that's the whole idea. You just follow the definition of matrix multiplication. So their product has at most S squared non-zero entries in each row and column. Okay, and that's actually all we need to prove this fact. So when we look at A times B, we can expand it out in terms of LA and SA and LB and SB like this. And we get a sum of 3 matrices. The first one over here, we just said has at most S squared entries, non-zero entries per row or column. And I claim these other 2 terms are low rank matrices. This one is low rank because L sub B is low rank, and the rank of the product of 2 matrices is always at most the minimum of the 2 ranks So this one has to have rank at most R. And similarly, this matrix here has LA in it, so its rank is at most R. And so this gives exactly the decomposition we wanted. The first two matrices sum to rank at most 2R, and the last matrix has at most S squared entries per row and column. So that proves this lemma. Yeah, any questions about that? Okay, so that's a really nice property of rigidity. And one particular corollary, I guess, that I want you to take away from this is that like these blowups in the parameters here are negligible when we're talking about valiant rigidity. So if A and B are not valiant rigid, then neither is their product. It's because if they're not valiant rigid, that means you can change n to the epsilon entries in each row and column to make its rank a little bit sublinear for both the matrices. So then applying this lemma, we get that in the product, you can change n to the 2 epsilon entries in each row and column to make its rank sublinear. And you just half whatever your epsilon was before, and you get the same type of result that you wanted. So in other words, if you take the product of a constant number of non-valiant rigid matrices, you get a non-valiant rigid matrix. Okay. So in diagonalization, we're actually going to apply that fact only in like a very particular way. Namely, the way I mentioned before, that if A is not rigid, then for every diagonal matrix D, A times D times A is not rigid. And this is just because, A is not rigid, D is not rigid because a diagonal matrix is not rigid. And so this is a product of 3 non-rigid matrices, which is hence not rigid. Why is this an interesting thing to look at? Well, as we're going to see soon, there are a lot of really well-studied matrices A, like a Walsh-Hadamard transform, the Fourier transform, the disjointness matrix, and some other examples that diagonalize big, important families of matrices. So this is going to give us a relationship between the rigidity of like some matrix we care about and the rigidity of another family of matrices we care about. But we'll see soon in a second. But I quickly want to mention, this can be seen kind of both as a rigidity upper bound tool and a rigidity lower bound tool. So you can actually use this to try to prove that the matrix A is rigid. So if you can prove that there exists a D such that A times D times A is rigid, then that would imply that using this result, that would imply that A itself is rigid. And that's a little bit interesting because in general, we have more techniques for proving that like many matrices in this big collection of matrices are rigid. Like, for example, we know how to show a random matrix is rigid with high probability. We have more techniques like that than we do for showing like this one particular matrix is rigid. But this is away from going from a result that says at least one of these many matrices is rigid to showing this one particular matrix is rigid. So you can see it as a rigidity lower bounding tool like this, but we're going to use it as a rigidity upper bounding tool. So we'll use it to go from the fact that we're going to cleverly pick a matrix A that it's not very hard to show is not rigid, and then use that to show that a big family of matrices is not rigid. And we'll see that there are nice matrices in that family. That's the idea. So the particular matrix I promised you we'd show is not rigid is called the Walsh-Hadamard transform. Here's its definition. It's a recursive definition. So the first one is a 2x2 matrix with 3 1s and a -1. And then each subsequent one is 4 copies of the previous one where you negate the top right one of them. So the Hn is a 2 to the n by 2 to the n matrix. And here's a picture of some of them, the first 4 of them. Okay, so why is it interesting to study the rigidity of these? Well, let's let capital N be the side length of the matrix. So capital N is 2 to the little n. Then it's known that the Walsh-Hadamard transform has an n log n size log n depth linear circuit. This corresponds to an algorithm. It's called the fast Walsh-Hadamard transform. But if you're familiar with like the fast Fourier transform, it's actually a simpler version of that algorithm. And this algorithm is widely believed to be optimal, at least up to constant factors, let's say. So one avenue toward trying to prove that it's optimal would be to show that it is a valiant rigid matrix. So as I said, that would rule out the existence of linear size log depth circuits for it. So it wouldn't prove it's optimal, but it would prove something toward proving that it's optimal. So the result I'm going to show you is actually that this avenue toward proving that the Walsh-Hadamard transform, a circuit lower bound for it, actually can't work. So I'll show the result joint with Ryan Williams is that actually for any field F, the Walsh-Hadamard transform is not valiant rigid. So for any epsilon, you can change epsilon and n to the epsilon entries per row and column of the matrix to drop its rank to this quantity, n to the 1 minus about epsilon squared. And so this is actually even stronger than what we need to prove that it's not valiant rigid. Like to show it's not valiant rigid, you would just need to show that you can change n to the epsilon entries per row and column to make its rank a little bit sublinear, like n over log n. But here we're actually going to get all the way down to rank n to the 1 minus like epsilon squared. So actually it's like even less rigid than just not valiant rigid. Okay, so that's what I'm going to prove. And you'll recall I promised I was going to prove an even more general statement. So let me tell you about the even bigger family of matrices I'll prove is not rigid. I'm calling them or and matrices. I just made up these names. So I don't know if they have a different name in the literature that I don't know about. But here's their definition. So they work over any field, and they're parameterized by a function f that takes n-bit Boolean strings to elements of the field. So take any Boolean input f-valued function. Then we define the or matrix for f, which I'll denote with like an or in the superscript there, and the and matrix for f that I'll denote with an and in the superscript there. And these are 2 to the n by 2 to the n matrices. And they're defined like this. So for row x, which is a 0, 1 vector of length n, and column y, which is a 0, 1 vector of length n, the xy entry of the or matrix is f applied to this is like the bitwise or of x and y. And similarly, the and matrix is f applied to the bitwise and. So you take the row index and the column index, you do the bitwise or and of them, and then you apply the function. And that's how you define these matrices. Okay, so first of all, we can check that the Walsh-Hadamard transform is an example of one of these. So in fact, the Walsh-Hadamard transform is an and matrix. It's the and matrix for the parity function. So the parity function is defined like this. It's just the -1 to the power of the number of ones in its input vector. So the Walsh-Hadamard transform is you take the bitwise and then you take the parity of the number of ones in that. So just here's the like recursive definition of the Walsh-Hadamard transform again, and you can like label the rows 1 and 0 and 1 and 0, and now what's happening is that if both of these bits are 1, so if the and is 1, then you like negate the recursive call, and otherwise you like leave the recursive call as it was. So you're really taking each time the and of the 2 bits is 1, you're negating the output. So you're taking the parity of the and of all these bits. Okay. But this is kind of like almost one of the simplest non-trivial examples of an and matrix. Like the parity function is a pretty simple Boolean function. I'm actually going to show that these matrices are not rigid, even if f is like a totally random Boolean function like this. So there's actually a much bigger class of matrices that I'll prove is not rigid. Let me mention this quickly first. So actually, and matrices and or matrices, I'm going to talk about both of them for like notational convenience, but they're really the same thing as each other. If you just like swap the meaning of 1 and 0 in the definition of the function and the definition of the indices, it just swaps between a and matrix and a corresponding or matrix. So they're really just like permutations of the rows and columns of each other. Yeah, and so what we're going to prove is that for every function f over any field, the and matrix is not valiant rigid. And if you're familiar with the original proof that the Walsh-Hadamard transform is not rigid, I think this is a little bit surprising because the original proof made use of the fact that the parity function is quite simple and has a polynomial, a very low degree polynomial approximation, I guess. And so in fact, we're going to see in some sense that property of the parity function was not needed for the rigidity upper bound. So this is really a more general result. Okay, so let's get into it. So the proof technique that I said we're going to use is this diagonalization technique. So I want to show that every AND matrix is diagonalized by some particular simple matrix. And the simple matrix I'm going to use is, so we want to show that for every AND matrix, there's some diagonal in the matrix such that M sub F is diagonalized by this matrix R sub N that's, I'm going to call the disjointness matrix. So this is a matrix that probably most of you have seen before. It comes up in lots and lots of different contexts. Like one definition is it's the communication matrix for the disjointness function, which is why I'm calling it the disjointness matrix. But it's also, it has a nice recursive definition. It's like the Walsh-Hadamard transform, but with zeros instead of -1s in it. So this is a 2 to the n by 2 to the n matrix, but it has only 3 to the n ones in it. So it's a pretty sparse matrix. You can also see it as an OR matrix. It's actually the OR matrix of the AND function. And to see that, I think we once again label the indices like 1 and 0 and 1 and 0. And you can see that if the OR is false, then we're going to output 0 at the end. Otherwise, we're going to go to the recursive call. And so if there's any bit where both of them are 0, then we output 0, and otherwise we output 1. So it's the OR matrix for the AND function, like the AND of the bitwise ORs. Okay. There's more definitions. I'm not going to say all of them. I kind of like this one because it reminds me of the orthogonal vectors problem from like fine-grained complexity. In fact, there's some sense in which the non-rigidity of this matrix is used in algorithms for that problem, but I probably won't get into that today. Okay, but anyway, this is the matrix we're going to look at. And then the plan for our proof is that we're going to show first that this factorization is true, that every AND matrix is diagonalized by the disjointness matrix. And then I'm going to prove that the disjointness matrix is not rigid. And the proof that the disjointness matrix is not rigid is going to intuitively be pretty easy because the disjointness matrix is so sparse to begin with. Like we're supposed to show that it's a sum of a sparse and low rank matrix, but it's already almost so sparse enough, so it'll be pretty easy. So that's the idea. Okay, so let's start with step 1, the proving that this R sub n does diagonalize AND matrices. So here's a reminder of the definition of the matrices we're talking about. So the AND matrix, its x comma y entry is f of the bitwise AND of x and y, and R sub n of xy is AND of the bitwise OR of x and y. Okay, and I want to show that R sub n diagonalizes this. So let's start by writing out what happens when you compute R sub n times a diagonal matrix times R sub n. Okay, so say you have some diagonal matrix D. What's the x comma y entry of R sub n times D times R sub n going to be? Okay, well, first of all, we could just expand this out, again, using the definition of matrix multiplication. Putting a diagonal matrix in the middle doesn't really make a difference. It's just the sum over Z of the x comma Z entry of R sub n times the ZZ entry of D times the ZY entry of R sub n. This is just the definition of matrix multiplication. Okay, now what I'm going to do, so these R sub n of xz and zy. So remember, R sub n, all its entries are 1 or 0. So I'm going to just move the condition that these are equal to 1 into the subscript of the sum. So I'll write it like this. So it's just the sum over all the z's such that these two values are both 1 of D, the ZZ entry of D. So, and the condition for when those are 1 is just the first one is that the AND of the bitwise OR of x and z is 1, and the second is that the AND of the bitwise OR of y and z is 1. Okay, so I just moved the condition that those are both 1 into the subscript there. Okay, now here's probably the trickiest step of the whole proof. We're going to rearrange this logical statement a little bit. into a different equivalent logical statement. So here it is. So I claim that the and of x or z and the and of y or z are both true if and only if the and of x and y or z is true. Okay, let's write out the definitions of these things just to make sure we all agree these are the same thing. So at the top we're saying that, so since we're doing an and in the beginning, we're saying that for all of the entries of the vectors, either xi or zi is true. That's what this one's saying, and yi or zi is true. That's what this one's saying. So that's what the top is telling us. Okay, so let's rewrite this a different way. It's the same as saying that for all I, well, either zi is true, or if not, then xi and yi both have to be true for this top thing to be true. So zi or xi and yi have to be true. So these are like equivalent to each other. And then this is just what I wrote here. So for every bit, zi is true or xi and yi are true. So that's why these two are the same as each other. Okay. And now that we've written that, that's kind of where the x and y that we're going to need is going to come from. So now we just need to rearrange some things. And write definitions. Okay, so we can once again move this condition back as an r sub n of something. So we can say this is again just the sum over all z of r sub n of x and y comma z, because we have the x and y here. Now we're going to actually pick what D is going to be. Okay, so let's say D is a diagonal matrix. Let's say little d is the vector of the entries along the diagonal. Okay, so this is just the sum of r sub n of x and y comma z times entry z of the vector D. Okay, and now when we look at this that we have here, this is exactly picking out some entry of the matrix vector product r times D. Okay, so this is exactly equal to r times d, the x and y entry of that vector. So let's pick it d so that this is going to be exactly what we want. So here's how you do it specifically. I'm going to make one vector v sub f be just the vector of the outputs of the function f that we care about over here. So this vector is just like the truth table of the function f. And I'm going to define d to be r inverse times v sub f. It's not hard to see that r is invertible over any field. So you can define it this way. So then, okay, we add r sub n times d. That's just equal to v sub f. It's the x and y entry of v sub f, which we just defined to be f of x and y, which is the corresponding entry of our matrix. Okay, so that's, okay, there's a lot of steps, but really there was one actual idea, which is showing these two expressions are equivalent to each other. Okay, so that proves that r sub n, it diagonalizes all the and matrices. So all that's left is to prove that r sub n is not rigid. And then we will show that all the and matrices are not rigid. So let's do it. So here's just, I'm going to keep a reminder of the definition of r sub n at the top. So just a reminder, the intuition is that r sub n is a really sparse matrix to begin with. So it's not sparse enough to just immediately say it's not rigid, but it is sparse enough that we're going to modify it just a little bit to make it not rigid. And the idea is that we're going to show that most of the non-zero entries of r sub n are actually confined to just a few densest rows and columns of the matrix. Okay, so here's more precisely what we're going to show. For any positive integer k, we can remove n choose less than k rows. By that, I just mean the sum from I equals 0 to k minus 1 of n choose I. That's what I mean when I put like an inequality inside a binomial coefficient. So we can remove that many rows and that many columns from r sub n, so that what we're left with is a matrix where each row and each column has at most n minus k choose greater than or equal to k non-zero entries. So you'll have to believe me, these, like, we're going to pick k at the end so that these numbers are all quite small numbers. Okay. Okay, so let me prove this. And it's going to be like a basic counting argument. So here's the proof. What we're going to do again is remove the densest rows and columns from the matrix. So we're going to remove the rows corresponding to x such that x, sorry, by absolute value of x, I just mean to n of x, the number of ones in the vector x. Okay, so we're going to remove the rows corresponding to x that have more than n minus k ones, and remove the columns corresponding to y that have more than n minus k ones in them. So intuitively, these are the densest ones because they make it easiest for this and of ors thing to be true when they have a lot of ones in them. Okay, it's like immediate that this is the number of rows and columns that we're removing. I mean, okay, maybe it looks more like n choose greater than n minus k, but that's equal to n choose less than k by symmetry. Okay. So now we just have to check that each row afterwards, each row and each column has at most n minus k choose greater than or equal to k non-zero entries in it. So let's let x be a row that we didn't remove, which means the number of ones is at most n minus k. So we're asking how many columns are there that we didn't remove and that have a 1 in that entry of R. So in other words, how many y are there that also have at most n minus k ones, and such that the and of x or y is 1. Okay. So, well, let's draw what our vector x looks like. Here it is. It has like it has some number of ones in it. I'm gonna, without loss of generality, just put them all at the very beginning, and then it has some number of zeros in it. And we know by assumption it has at most n minus k ones. So the length of this is at most n minus k. Okay. So first of all, yeah, and then let's figure out what y has to look like, given that this is what x looks like. So first of all, in each entry where x is 0, we have to have y is 1. We have to have ones in all these entries. And this is because the and of x or y has to be true. So in every entry, at least one of x or y has to have a 1. So in the entries where x has a 0, we have to have y has a 1. Okay. Now, in the other entries, there's at most n minus k of these other entries. And we have to remember that y has at most n minus k ones in it. So there's at least k zeros here. Yeah, at least k zeros in the rest of the vector. But otherwise, it's unconstrained. We can put any zeros and ones there, and it doesn't matter because x already has ones. But just that's enough to give our bound, because the number of choices of y like this is just the number of entries here. N minus k choose the number of zeros we're allowed, which is at least k. So that means there's at most n minus k choose greater than or equal to k non-zero entries in row x. Okay, so that's the proof of the lemma. It's like a simple counting argument. Okay, so now finally, let's put it all together and use this lemma to prove that R sub n is not rigid. So here's the idea. That this is what we're trying to prove, just as a reminder, that R sub n is not rigid. So we're going to apply the lemma with k is half minus epsilon times n. So k is going to be just a little bit less than n over 2, like the middle possible value. Okay, so what happens when we do that? Well, in the first part of the lemma, we're removing n choose less than k rows and columns. So that's, well, we can compute what n choose less than k is. It's n choose less than half minus epsilon n. And by like a standard tail bound, the binomial coefficients, well, let me draw a picture. K and choose k. They're like really heavily concentrated around n over 2. So they really look like this, and then like a big peak right in the middle. Okay, sorry, this is not a great drawing. But if you go even just like a little bit epsilon to the left, you already like substantially decrease how big the binomial coefficient is, or epsilon times n. Oh, I just erased it. Sorry. If we go epsilon times n to the left of where we were, it substantially decreases. And you can show, like using standard tail bounds, like a Chernoff bound, that actually this will be less than n to the 1 minus something like epsilon squared. Okay, so you can remove this many rows and columns from the matrix to make it sparse. But the important point here is that removing rows and columns is the same as making low rank updates to the matrix. So whenever you remove, let's say, one row or column from a matrix, that actually changes the rank of the matrix by 1. So one easy way to see this is like if you remove a row, you can think of just adding that row to the like set of vectors that span the row space of your matrix. So you increase the rank by 1 to make up for the fact that you deleted that row. So if we remove just this many rows, we're changing the rank by only this amount. And then what we're left with is a sparse matrix where in each row or column, the number of zero and non-zero entries is at most n minus k choose greater than or equal to k, which is half plus epsilon n choose at least half minus epsilon n, which is the same as half plus epsilon n choose at most epsilon times n, which is at most n to the epsilon. By capital N, I mean, sorry, by capital N, I mean 2 to the little n here. Yeah. By, again, standard bound on the binomial coefficient. So that's actually it. Just this lemma about removing the densest rows and columns is actually enough to just show that the matrix is not valiant rigid. Okay, and that's the end of the proof. Okay, so before I move on to the second proof, are there any questions about this?
Looks like no. Yeah, and I don't see any questions on the chat either.
Excellent. That's well, okay. Maybe I'd normally like questions, but I think I might run out of time, so maybe it's better that there are no questions. Okay, so let's move on then to the second technique I want to tell you about today, the polynomial method, where the idea is to show that if the entries of a matrix are computed by a low degree polynomial, then that means the matrix is not rigid. Okay, so I'll just tell you right away the result we're going to prove, because it'll be interesting to compare it to the previous result we just proved. So this is a result by Zev Devere and Ben Edelman, where they showed that for any finite field FQ and any function f that maps vectors over FQ to values over FQ, the q to the n by q to the n matrix M, given by this f of the sum of the row index and the column index, is not rigid. So let me just compare this to the result we just proved. So before we were talking about any field, here we have to restrict ourselves to a finite field. The function we are talking about, before we were talking about a Boolean input function. Here we're instead talking about a function that takes in vectors from FQ to the n. So instead of vectors of zeros and ones, we're taking vectors of elements from the field FQ. And so as a result, the matrix we're looking at, instead of being a 2 by 2 matrix, is now a 2 to the n by 2 to the n matrix, is now a q to the n by q to the n matrix. So I'll clear the lines. I think they're kind of clogging it. And then finally, what the entries are given by f of the sum of the two indices. Before we were looking at like the bitwise and or the bitwise or. Now we're looking at the entry-wise sum of these FQ values, or in other words, just summing x and y over the vector space FQ to the n. Okay, so it's like kind of similar looking to the matrices we were looking at before, but it's also a little bit different. And what we are going to prove is that these matrices are not rigid, not valiant rigid. And I do quickly want to mention before we get into it that there is follow-up work by Zev Devere and Alan Liu that generalized this result, which I'll talk about a bit later. So I'm not proving now the most general known result along these lines, but this proof I think shows off the polynomial method better, which is why I picked it. Okay, so here's the proof outline. We're going to show that this function that defines our matrix, we're going to show that it has a low degree polynomial approximation. And then we're going to show that the fact that it has a low degree polynomial approximation means that the matrix is not valiant rigid. Okay, that's the idea. And actually, even though I presented this as step 1 and step 2, I'm actually going to start by telling you about step 2 first. So I'm going to start by telling you about the polynomial method and how it gives rigidity upper bounds. And then we'll return to this specific function. Okay, so we're going to be talking about multivariate polynomials over FQ. So let me give a definition about that we're going to have to use. So here it is. Okay, there's lots of parameters, but I'll like remind you what they are every time they show up. So hopefully it won't be too complicated. So I'm going to write M sub n dq to be the number of monomials in n variables of degree at most d over the finite field FQ. Okay, or equivalently, it's the number of, we can write in this like more mathematical way I wrote above. It's the number of monomials in n variables where its degree is at most d. So that means the exponents sum to at most d. And it's over FQ. So that means each of the exponents is an integer between 0 and q minus 1. So you can check like by Fermat's little theorem that when you're working with polynomials over FQ, you never need to take any variable to a higher power higher than q minus 1. Okay, so it's the number of these. This is just like, I'm sure you all could write some expression with binomial coefficients and stuff that computes what this number is. I'm not going to write it out just to simplify things a bit, but I think you all like could do that if you wanted to. Let me like mention a tiny bit of intuition about this number though. So the tiny bit of intuition that's going to be useful for the proof is that for fixed q and big N, the number of degree d monomials looks a lot like a normal curve centered around like half of the maximum possible degree. The maximum degree is n times q minus 1. So they'll look like a normal curve centered around n times q minus 1 over 2. So it's just like the binomial coefficients we were talking about before. We have d, we have m sub n d q, and it looks like this, where like at the middle at n times q minus 1 over 2 is halfway, and it's like symmetric around that, and almost all the mass is in the middle. If you go just a little bit to the side, it drops a lot. Okay, that's the main intuition you need to know. And for example, we can check that when q is 2, this thing is actually exactly the binomial coefficient n choose d, which we already know behaves in this way. Okay, that's all we need to know about that. I'll remind you of this stuff when it comes back. So the polynomial method, to explain it, I'm actually going to first state like a slightly different characterization of rank than you're maybe familiar with. Actually, I think this is exactly what you're familiar with, but maybe I'm like writing the notation a bit different. So I want to talk it over anyway. So it's that a matrix has rank at most R if and only if there are functions f1 through fr and g1 through gr, such that for every row x and column y, the x, y entry of the matrix is the sum from I equals 1 to r of fi of x times gi of y. So the matrix has rank at most R if and only if there are these 2R functions, so that you can write the entries of the matrix in this way. And this is just, if you don't immediately recognize this, it's just, so if M has at most rank R, then that means you can write it as the product of an n by R matrix times an R by n matrix. And the Fs are just going to be like the columns of the first matrix, and the Gs are just going to be the rows of the second matrix. And you can check that when you do that, this definition exactly works out. But when you think of it as functions like this, it becomes clear very quickly that, I'll erase the picture. It becomes clear very quickly that polynomials give rise to rank upper bounds. So here's the statement I want to prove. If P is a polynomial in 2n variables and it's degree d, then you define the matrix like we've been defining it. It's the q to the n by q to the n matrix, whose x, y entry is just P evaluated at x and y. Then the rank of this matrix is at most this, the number of monomials of 2n variables of degree at most d. Okay, why is this? Well, this quantity m here, this is exactly the upper bound on how many monomials P itself might have. P is a polynomial in 2n variables. It has degree D, so it has at most M 2n dq monomials. Okay. And the key remark is that each monomial is of this form f times g that we want. So this is, I think, easiest seen just with an example. If you look at the monomial, you split it up into the x part of the monomial and the y part of the monomial like this. And it's exactly of the form f of x times g of y like we wanted. So each monomial corresponds to a rank 1 matrix, and the polynomial corresponds to a matrix whose rank is at most the number of monomials, which we can at least bound in this way. Okay, so it's like a simple but really nice remark showing that if you can approximate the entries if you can compute the entries of a matrix by a polynomial, then you get a rank upper bound on the matrix. Okay, but I'm actually going to need a slight strengthening of this lemma. So let me state that now. This is a lemma that was it was famously used by Kroot, Lev, and Pak to prove, toward proving the capset conjecture in extremal combinatorics. So the setup is almost the same as the lemma from the last slide. We have a polynomial in 2n variables. It's degree D, and we make the matrix given by P, the x comma y entry is P of x comma y. But now I'm going to prove a slightly better rank upper bound. So before I had I had a 2n here and I had a d here. So I've improved the n and the d by factors of 2. So I'm going to show the rank is at most twice. Well, there's a new 2 over here also. Twice the number of monomials of a polynomial with just n variables of degree d over 2 over fq. Okay? So these factors of 2, in many applications, they don't really matter. But actually, in the proof I'm telling you today, they're going to matter a lot. So I'm going to just tell you this step. Okay, so here's the idea. The main idea is just that in every monomial of degree at most d, at least either the x part of the monomial or the y part of the monomial has degree at most d over 2. Okay, and we're going to group them together like that. So we're going to group together monomials that have the same low degree x part or the same low degree y part into the same f of x times g of y term. And once again, I think this is easiest to see with just an example. So here's, I leave myself much space. Here's three monomials that each have the same x part, x1 times x5, but 3 different y parts. And in our proof from the last slide, we would have counted this as rank 3 toward the sum of ranks at the end. But actually, if we group together these 3 monomials as the x part times the sum of the y parts, then we get rank only 1 for these 3 monomials together. So instead of needing a 1 term for every single monomial, we only need 1 term for each x part of degree at most d over 2, and 1 term for each y part of degree at most d over 2. So we'll get twice the number of monomials in just n variables, because it's just x or just y variables, of degree d over 2. Okay, and this will end up making, this factor of 2 thing will end up making a difference at the end. But if you didn't exactly follow it, it's okay to just think about the previous slide. Okay, so let's try to apply it then to our function f of x plus y. So here's a reminder of what we're trying to prove. I'm not going to say it again, but we're trying to show that the matrix f of x plus y is not rigid. So a simple remark, for any function f, it can be written as a polynomial of a degree at most n times q minus 1. This is just, any function can be written as some polynomial, and this is the maximum possible degree of any polynomial over fq in n variables. Okay, so we can just take this degree bound and directly plug it into the rank upper bound from the previous slide. And it says m has rank at most twice the number of monomials in n variables of degree, the maximum degree over 2. But of course, when you work this out, this is just equal to q to the n, which is the trivial upper bound, because we're talking about a q to the n by q to the n matrix. This is because by symmetry, exactly half of the matrix of the monomials have degree at most n times q minus 1 over 2, and the others have degree bigger than that. Okay. Okay, but in some sense, we couldn't have hoped for this to work because we're only proving a rank upper bound right now, and we're not really using the full power of rigidity. And it's not hard to check that there are functions f such that the matrix M does have full rank. So we couldn't have hoped for this to work just like that. But what I'm going to do is show that there's a lower degree polynomial, which usually agrees with f. And then I'll use the lemma from the last slide to show that this lower degree polynomial gives rise to an actually low rank matrix. And it won't differ from M in too many entries because this new function will usually agree with f. Okay, so here's the polynomial approximation lemma I'm going to prove. Here it is. So if for any function f and any degree d, there's a degree d approximation of f. So by which I mean a function g, it's also from fq to the n to fq, such that g has degree at most d as a polynomial, and f and g agree on at least m sub n dq inputs. So the number of inputs on which f and g agree is at least the number of monomials in n variables of degree at most d in fq. Okay, so the intuition for this is that so we can like pick g to be any polynomial from the vector space of polynomials of degree at most d, and the dimension of that vector space is exactly the number of monomials of degree at most d. So kind of this number is like the dimension of the vector space we're picking g from. So we should somehow have that many degrees of freedom to get it right on that many inputs. That's the intuition, and I'll show you that intuition just exactly works out basically. So here's the proof. You consider the q to the n by m matrix that maps the coefficients of a degree at most d polynomial to the q to the n possible outputs of that polynomial. So this is like it's a q to the n by m matrix, and the rows correspond to like inputs in fq to the n. The outputs, the columns, correspond to monomials of degree at most d, and then like the entry is going to be the the monomial evaluated at that input. And you can check that when you take this and you multiply it by the vector of the coefficients of a polynomial, it evaluates that polynomial at all the possible inputs. Okay, so here's this matrix. First of all, all the columns of this matrix are linearly independent. Why is that? Well, if it weren't the case, then you would have a non-trivial linear combination of the monomials that output 0 on every possible input. So in other words, you'd have a non-zero polynomial that outputs 0 on every input, which we know can't be the case. So the columns are linearly independent. So that means there has to be a full rank m by m submatrix somewhere in this big matrix. Full rank. Okay. And I claim then that we can always get the outputs corresponding to the rows in this full rank submatrix right. So whatever the values f is supposed to take just on these entries here, we can always pick an input vector so that when you multiply it by this full rank matrix, you get the target vector that you're aiming for in just these m rows. So we can always pick a degree at most d polynomial which agrees with f on these m entries. So which is exactly what we were trying to prove. So actually it's a little bit stronger. It's always the same entries that you get it right on for a fixed degree d. Okay, so that's that. And finally, I think I'm about out of time. Let me try to finish quickly. So let's just put everything together. So we have two lemmas that we proved. The first just now is that any function has a low degree approximation that agrees on a lot of inputs. The second lemma is that low degree polynomials give rise to low rank matrices. And we want to combine them to show that the matrix for the function f of x plus y is not rigid. So we're just going to apply this with degree remember before we tried applying like lemma 2 with the maximum possible degree, n times q minus 1. Here we're going to apply it with just a slightly less degree. So like 1 minus epsilon prime times n times q minus 1. Maybe I'll kind of skip the details of what happens here, but you know, by lemma 1, we know that f and g agree on almost every input. So, you know, remember there's like the picture that looks like this of how many monomials are there of a certain degree. So the number of inputs that f and g disagree on is just like the difference between this point here and this point here, which by like standard tail bounds on these binomial coefficient like things is you can bound by, if this is only epsilon n to the left, then it'll be only epsilon prime n, then there'll be only q to the epsilon n points that they disagree on. And for every in every row of the matrix M, like every output of f is used exactly once and every output of g is used exactly once. So the number of entries where f and g disagree is exactly the same as how many entries per row and column these two matrices disagree on. Okay, and then you apply the lemma 2, and it says that the matrix for G is not too high rank. It's just, again, you go epsilon to the side here, and it gets a lot smaller. And so these together imply that this matrix is not rigid. And that's the end of that proof. Satya, do I have one more minute, or am I out of time?
Yeah, go ahead. It's fine, Josh, since there are no questions, and I think, it's okay. Taking 1 or 2 more minutes is fine.
Okay, I just have one more slide.
That's fine.
So I just want to talk a little bit about what else is known beyond what I said today. So I mentioned there's this paper by Ziv, Devere, and Alan Liu, where they show that some more matrices are not rigid. They show that any Fourier transform is not rigid. I won't read out the definition, but if you haven't seen it before, here's what a Fourier transform is. They also show that any group algebra matrix over any field and finite abelian group G is not rigid. So that's defined like this, that now we're taking functions from any group to the field, and you make a size of the group by size of the group matrix, whose entries for A and B are, where A and B are elements of the group. You apply the group operation to them and then take f of that. So this generalizes the matrices we were just talking about. And when the group is fq to the n, then this is exactly the same definition we were just talking about, but you can extend it to any finite abelian group in this way. And they show that these matrices over any field are not rigid. So that includes the results we were just talking about. It also includes circulant matrices and other matrices. And actually, the techniques they use to prove these results are pretty similar to the techniques we talked about today. So they prove that the Fourier transform is not rigid using the polynomial method. And then they prove that group algebra matrices are not rigid by showing that roughly that Fourier transforms diagonalize group algebra matrices. So that's, I mean, I'm a little bit oversimplifying what they do. It's a really nice paper, you should read it, but they do at a high level use the same techniques we talked about today. And then I quickly want to mention a few things that I think might come next in this line of work. So first of all, just talking specifically about this result I just mentioned, it'd be interesting to study whether non-abelian groups can give rise to rigid matrices or not. So Devere and Liu specifically mentioned that they think quasi-random groups will be hard to resolve because of the representation theory of these groups. But if you're interested in this stuff, it might be a nice set of groups to look at. I also think one thing that's interesting is in the two proofs, kind of the same, you might have noticed the same kind of tail bounds showed up. And like the arguments we've been using naturally give rise to rigidity upper bounds with certain parameter regimes, but not other parameter regimes. So I'd be interested to see if these or different techniques can give rigidity upper bounds in other regimes, such as like for Rasborov rigidity, like in the regime where you get communication lower bounds instead of like valiant rigidity where you get circuit lower bounds. Another thing think would be really interesting is more applications of non-rigidity, like taking these and getting other algorithmic applications out of them. And then finally, we should use all these results to find rigid matrices. Okay, that's all I have to say. Thanks.
All right. Thanks, Josh. And we may be able to have like maybe 1 or 2 questions if anybody has any. I don't see any raised hands, but yeah, we have just a minute or two to answer any questions.
I have one quick question, if that's okay.
Yep. Yeah, go ahead, Cyrus.
Hey, Josh.
Hey.
I was wondering if so there's this open question about proving that the Walsh-Hadamard matrix cannot be approximated by sparse polynomials. This is like, and this would prove a lower bound for AC0 with parity at the bottom. It seems like that's still open despite all this progress.
Yeah, I think I don't remember off the top of my head. I think the parameters you would need for that are a little bit different from the parameters you get from these like polynomial method upper bounds though.
Yeah, exactly. And also the like row and column removal idea, I think breaks the sparsity of the approximation.
Yeah, for sure. Yeah, but maybe there's one more idea you can add on to the toolbox to get it to work.
Cool. Thanks. It was a great talk, by the way.
Thanks.
More questions? Maybe one more question.
Hi, Josh. This is Arkadev.
Hi, Arkadev.
Very nice talk. So you say that the Rasborov rigidity upper bounds, for communication complexity. So do you expect the Walsh-Hadamard matrix, or the in other words, the inner product matrix to not be Rasborov rigid? Is that your sense?
I've learned my lesson about expecting matrices to be rigid or not rigid. So I don't want to rule either way on that. I've tried a little bit to prove that it's not Rasborov rigid, and it's not clear to me how to use just the techniques we know right now. But I am a bit hopeful that maybe you can modify them a little bit to prove something. But I mean, maybe the reason I haven't been able to prove it is because it really is rigid. So I'm really not sure.
Okay. Thanks.
All right. So thank you, Josh, again. Thanks very much for the fantastic talk. So guys, we are pretty late on time, but that's okay. Hopefully everybody's okay, running a little bit late. So we will take a 10-minute break. I mean, we don't want to compromise on breaks. What we will do is we'll get back here 10 minutes from now. That would be 9:20 India time. And just add 10 minutes to wherever you are, and come back here in 10 minutes for the next talk by Ben Lee. Right? Okay. See you guys back here in 10 minutes.
Hi, Bentley. Can you try sharing your slides?
Sure, yes, I can do it.
Can you go to the next slide?
Yes.
Okay, sounds good. Yeah, I think so.
Okay, we'll start in about a minute, Bentley.
Okay, I'll just leave it.
Yep. All right, so let's start. Let's get to the second talk of this day today. Yeah, sorry, the morning doesn't sound appropriate for some locations. So in any case, so we have Ben Lee Vogt giving the second talk today. Ben Lee is a postdoctoral fellow at UT Austin, and previously he was a CMI postdoc at Caltech. Before that, he received his PhD from Tel Aviv University, advised by Amir Shpilka. Ben Lee is interested in complexity theory, in particular algebraic complexity, algorithms for algebraic problems, error correcting codes, and pseudorandomness. Today, he's going to tell us about polynomial degree upper bounds on equations for non-rigid matrices with applications to circuit lower bounds. Ben Lee, go ahead.
All right, yes, thank you. So I will just start. This is based on everything I'm going to say is based on a joint work with Renal. Let me also just say that again, if you have a question, just jump right in. I won't be able to read the chat during the talk. So no, if you want to
I will monitor that.
The chat is a perfect place, but just ask questions. Okay, so I will not, you've seen enough definitions of what is rigidity. I will not need to repeat it again. Let me just mention something which is, I guess, a slightly subtle point. For this talk, we'll think about rigid matrices over the complex numbers. The definition is the same. There's nothing special about that. Everything I will say also makes sense of a positive characteristic, but let's just not worry about it. It will be much easier over the complex number. Now, over the complex number, when you talk about explicit matrices, we still insist that there will be something you can construct in polynomial time. In particular, it means that the entries of these matrices should be integer numbers or rationals with small bit complexity. Of course, by scaling, you can just scale them and assume they are integers. And this is something which is kind of an unfair game, because what we are fighting against are decompositions which can contain arbitrary and crazy complex numbers. So, first thing you want to do when you have such a thing is to verify that there are rigid matrices. And the counting argument we saw yesterday don't quite work. Because, well, I mean, even, we're looking at a finite space of matrices. And even there are infinitely many rank 1 matrices over the complex numbers. But it's still true that there are rigid matrices. There are even 0-1 rigid matrices. And this is also proved using a counting argument. You just need to know what to count. So there are by now fairly standard techniques to do it. I put here two references which prove this explicitly. Anyway, the point of all this discussion is that we are working over the complex numbers. We look for rigid matrices that are explicit, and it means that in particular their entries are integers. And even though this technical introduction is needed, I guess, I still feel, and I think many others as well, that constructing rigid matrices should be easier over the complex numbers. So it's not it's not harder work for nothing. Okay, now that we got this out of the way, this talk is going to be about some approach to the study of matrix rigidity that comes from algebraic geometry. There will be nothing fancy mathematically in this talk. Everything will be very simple, except I will introduce some very elementary terminology in the beginning. And the point here is that we have this subspace of n by n matrices, or again over the complex number. And inside this subspace, this space, we have this set of non-rigid matrices, and we don't understand it very well, how it looks like. It has this crazy shape. I mean, what we know is that it's maybe a bit complicated, it's not nice. And we do know that it's small. This is, again, this counting argument I alluded to. There aren't many non-rigid matrices. And so this is a complicated set. And well, the first thing that we like to do is to take its closure. So now we have the closure of non-rigid matrices. And we have a closure, and it is something that we call a variety, and it has polynomials vanishing in it. And the question is, what can we say about those polynomials that are zero on the set of non-rigid matrices, or on the closure, the set of non-rigid matrices? And if it's not clear, I will soon define everything a bit more slowly. And so, of course, the zero polynomial is there, but the zero polynomial is not helpful because it's zero everywhere. But a non-zero polynomial that is zero on all non-rigid matrices already gives us something. So, okay, so let me define some basic terminology when we deal with those objects. So let me define what is called a variety. A variety in C to the n is just a set which is a common zero set of some polynomials. So V is a variety if there are polynomial f1 to ft, such that V is all the x's where all of these polynomials are zero. This is a simple definition. And each variety corresponds to an ideal, which I denote by I of V. So if you have a variety, I of V is just the set of polynomials that is zero on this variety. And this is an ideal because it's easy to verify that it's the sum of two things, the sum of two polynomials in this set is again in this set, and it's closed under multiplication by any polynomial. And it also goes the other way around. Whenever you have an ideal, there is a corresponding variety, which is just the set of x's that are zero for all the polynomials in the ideal. So this is the correspondence between ideal and varieties. It's basic things. There is something that I sort of swept under the rug here, which is that whenever you have a variety, you can assume that it is defined by a finite number of polynomials. This is not completely obvious if you haven't seen this before, but it is still true. Okay, so these are ideals and varieties. And let me define the notion of closure. So now we have an arbitrary set, not necessarily a variety. And again, we can think of all the polynomials that are zero on this set. Right? This is again would be an ideal. When we look at the variety that correspond to this ideal, we call this the Zariski closure of the set A, and we denote it by this A bar. Let's there's a lot of words, so let's just think for a second slowly what it means. A bar is just the following thing. We look at all the polynomials that are 0 on A, and we look at the common zeros of those polynomials. So by definition, certainly this set contains A, but it can also contain other points, right? There are simple way to see it, and this set is a variety. This is by the set A bar, A closure is a variety. This is just by definition. It's also the smallest variety that contains A. And in algebraic complexity, it's very convenient to study those sets and their closure where A corresponds to the set of low complexity algebraic objects, like non-rigid matrices, which is what will happen in this talk, but you can also think of tensors of low rank. You can also think of coefficient vectors of polynomials that has small circuits. So all of these are just set in C to the n, and we can look at the sets and this closure, and we can try to understand it. And I will soon argue that this point of view is helpful for proving lower bounds. Let me just say that, again, this is a bit informal, but for such sets, it's usually the case that the closure in this sense of the Zariski closure is just the Euclidean closure. So if you want to imagine things in a picture, like I did in the previous slide, whenever I write A bar, you can just think of the Euclidean closure of A. Of course, it's not a formal theorem what I wrote here, because I mean, you can see just like you can think of it. There is a way to make it formal. You can think of it just as an empirical fact that for all of these sets, it turns out that the Zariski closure actually equals to the Euclidean closure, the usual closure of A with respect to the topology that you know. Okay, so how does this point of view helps us in proving lower bounds? Well, again, we have A being set of some low complexity objects, and when we have a non-zero polynomial in the ideal of A, we call it an equation for A. So recall that this I of A, this is the set of polynomials which are 0 on A. And we want, again, of course, the zero polynomial is always in I of A, but we want non-zero elements in this ideal, so we call them equations. And the point is that P, you can think of it as a proof that a point is not in A, right? Just by definition, if P of V is non-zero, then V is not in A. And if A is the set of low complexity objects, then P of V is non-zero means that V has high complexity. So this is what you call algebraic proof of a lower bound. And it's not hard to see that when P of V is non-zero, what you actually prove that V is not in the closure of A, right? A polynomial, or maybe a different way to say it, that a polynomial which is 0 on A is 0 on the closure of A. This is, for Euclidean topology, this is just by continuity, and for the Zariski closure, this is just by definition. So whenever you have this polynomial, it is not only 0 on A, it is also 0 on the closure of A. So P of V being non-zero means that V does not only have high complexity, it's not a limit of things with I mean, I'm sorry, it's not only that it doesn't have low complexity, it's also not a limit of things with low complexity. So algebraic proofs always give a lower bound for also the closure, not just the set itself. Okay, so of course we want it would be nice if P is simple in an informal sense, right? Because we want if P is simple, then maybe we can find P. And then maybe we can actually compute P on some points. And then if we can compute and it turns out that the result is non-zero, then we actually proved a circuit lower bound. And it's actually, you know, it's not completely theoretical. This is the setting in which many lower bounds in algebraic complexity are proved. Even if they were not proved in this terminology originally, you can read the proofs and figure out that this is in some sense what's going on. And there's a paper of, I should have cited it, there's a paper of Joshua Gocha, which actually spells it out for many models of algebraic computations. Okay, let me, before we resume to talk about matrix rigidity, let me make a small detour and talk about what we call algebraic natural proofs. It will only take a few minutes. So we say that the proof is natural if P has low complexity. Maybe I should add, we want P to have low degree and small arithmetic circuits. This is what we formally mean. So, you know, P is a natural proof if it's n. Recall that n is the number of variables of P, and we want it to have degree polynomial and have it be efficiently computed. And as I said, there are algebraic natural proofs for many limited model of computations. It's an open problem whether there are natural proofs for strong classes of algebraic computation, like polynomial size arithmetic circuits or other strong models. Yeah, so it's an open problem, and some people conjecture that they don't exist, and this corresponds to some natural proofs barrier for algebraic complexity, which is an interesting question, but something that we will discuss another day. And another way to think of it, of the question of whether there are algebraic natural proofs, is it is in some sense a quote-unquote MCSP problem for algebraic circuits or for algebraic complexity, in the sense that we ask, at least in the case for general algebraic circuits, we want to ask what is the complexity of deciding whether a coefficient vector has a small algebraic circuit, and we ask it in the model of algebraic circuit. So it has this meta complexity point of view, which is which also the same flavor as MCSP. Anyway, as I said, this is a bit of a detour. The main question, which is natural to ask, is are there natural proofs for rigidity? Right. So recall that we consider polynomials that have n squared variables, so they are polynomial over matrices, and we want those polynomials to be zero whenever a matrix is non-rigid. And we ask, are those polynomials easy to compute? So people have asked this before, and okay, so I guess the first order of business is to prove something. And the study of this algebraic geometry point of view of matrix rigidity was started in these two papers. So okay, so there are many names here. The names are Kumar, Lockham, Patankar, and Sama, and this is Gesmundo, Hauenstein, Eichenmeier, and Landsberg. And what they prove is that there is an equation of exponential degree, or let's write it in a bit more detail. So whenever S is smaller than n minus r squared, so this is a necessary condition for the existence of rigid matrices. If you remember yesterday, I think it came up in Ramia's talk that you can always change n minus r squared entries and get to rank r, but whenever S is small, you can ask for matrices which are not RS rigid. And they prove that there is some polynomial which is non-zero, and the degree is at most exponential in n. So I think this is the bound the first paper gets, and then the second paper improves it, but it's still exponential. one curious corollary of this thing that you can actually construct matrices which are, as we called them yesterday, semi-explicit, and they have optimal rigidity parameters, you know, really up to the exact numbers, right? It's the best you can hope for. And the idea is to take, you pick algebraic numbers, but algebraic numbers that don't have any low degree polynomial relations. So you can do it with roots of unity, with a large enough order, or probably there are other ways to do it. But one thing that they conjecture, at least the second paper conjectured, is that for some parameters you can do much better. In particular, they conjecture that for the parameters that are interested for proving circuit law bounds, so we want rigidity for, let's say, rank epsilon n and sparsity n to the 1 plus epsilon. So they conjecture that maybe you can get to the degree equation of degree polynomial n. And this would mean in some sense that this set of non-rigid matrices is, from a geometrical point of view, is not that complicated as these results would have you believe. You can think of this degree as one way to measure how complicated this set is. And what I'm going to show you is that this conjecture is in fact true. And the proof is quite simple. It doesn't use yeah, to prove this thing you need some something called elimination theory and Grabner bases. And to prove the new result, you don't need anything other than linear algebra, which I will just show you the entire proof. So, all right, let me write it. That there's an equation for matrices which are not, so it's even slightly better parameters. It's a rigidity with rank epsilon n and sparsity epsilon n squared. So there's an equation for matrices which are not that rigid, and the degree is at most, let's say, n cubed. You can slightly improve this, but it's not very important. Another thing that turns out to be true is that you can actually consider other varieties or sets of matrices that correspond to low complexity, and you can again prove a polynomial in n degree bound. So, for example, you can just forget about rigidity and just think about matrices that are computed by small linear circuits. And we prove that if you look at matrices computed by linear circuits of size at most epsilon n squared, epsilon here, or yeah, I guess epsilon is some constant. You can think of it as 0.01. So, of course, every matrix has a linear circuit of size at most n squared. But if you look at matrices that have a linear circuit of size at most n squared over 100, then you get a variety. If you take the closure, you get a variety, and there is some equation for this variety of degree at most polynomial in n. And you can do similar things for other algebraic objects, like a three-dimensional tensor of low rank or low slice rank or similar things. Okay, so this is the theorem that we will prove. One shortcoming of the proof is that it's a non-explicit proof. It doesn't give us an explicit equation. Explicit could mean that P, for example, has a small algebraic circuit, and we don't know whether it's true. Of course, if it turns out to be true, then this is great, right? Because now we would have this efficient algorithm that you just plug in something, and if it's non-zero, you know it's non-rigid, and this would be maybe make it very easy to come up with an explicit construction of a rigid matrix. If there isn't any explicit equation, then I claim that this is also somewhat good news, because now we have this pretty nice description of a hard family of polynomials. So I will return to this point at the end of this talk, but the point is that it really seems like a win-win situation in some sense, and we can also make this somewhat formal, this a win-win situation.
Benny,
But
just a quick
yes.
question. So does the degree bound get better if your epsilon gets smaller?
Yes, it should get better, but I mean, well, I guess when you're really close to the threshold, like we need epsilon to get small because at least I believe that when you really get close to the threshold, then maybe there's no reason to expect you would have polynomial bound on the degree.
No, I was wondering in your theorem, the first theorem is that does that n cube get improved if your epsilon gets small?
Yes, it does. I mean, you will see the proof. It's
okay.
Yes, it does get better. Okay, so now I guess let's just see the proof. Yes, so here's the theorem again, that there is a low degree equation for non-rigid matrices, where non-rigid mean with respect to rank epsilon n and sparsity epsilon n squared. The main lemma that we're going to prove is that there is some polynomial map, which I'm going to call Q. And Q is a polynomial map in a small number of variables. So the number of variables will be roughly epsilon n squared, or 4 epsilon n squared. And it outputs matrices. And Q is relatively low degree. And the image of Q contains all matrices which are not rigid. Right? This is the statement of the lemma, that you can find this polynomial map that takes as input a small number of variables and outputs matrices, and it's a low degree polynomial map. And the point is that the image of Q contains all matrices. And the lemma is really the main part. The lemma is also not hard, but let's just prove the theorem assuming the lemma for a moment. So the proof is okay. Let's think of two linear subspaces. One is the subspace of n squared varied polynomial of degree at most n cubed. This is the subspace in which we are going to find this equation that the theorem promises us. And the other is the subspace of polynomials on a smaller number of variables, for epsilon n squared, with a slightly higher degree. And the map is very simple. We just I'm going to describe a linear map between those subspaces. For every polynomial p in this subspace, I map it to p composed with q, where q is this fixed map from the lemma. So q is fixed. So this is a linear map, right? It's you just need to verify that you take a sum and you take multiplication by scalar and you show what you need to show. In any case, this is a linear map, and now let's compare the dimension of those two. So with the dimension of k varied polynomial of degree d, if degree at most d is k is this binomial coefficient, right? K plus d choose d, or let's just write it for this case. So here we have or n plus d choose n. That's another way to say it. So here we have n squared plus n cubed choose n squared, and here we have the number of variables plus the degree choose the number of variables. And the point of all this discussion is that the thing here is greater than the thing here when epsilon is small and n is large, right? Because this is standard ways to bound binomial coefficients. The point is that when you use the standard bound, here you would have this 4 epsilon n squared in the exponent, and here you would have n squared in the exponent, and the base would be some fixed polynomial in n for both of them. So this would be greater than this, and what it means is that this map has a non-trivial kernel, right? There is some non-zero polynomial here that when you compose it with q, you get the zero polynomial. And I claim that this P0 would be the equation, because whenever you pick a non-rigid M and you evaluate P0 of M, then M is a Q. I mean, this map contains in the image all non-rigid matrices. So M is Q of V for some V, and P0 of Q of anything is 0. So you would get 0, right? And that's it, right? I mean, there's no magic. So let me just summarize it. We found some non-zero polynomial that is has degree at most n cubed, and it is 0 on all non-rigid matrices. Okay, so we just need to prove the lemma at this point. And here it is the lemma, that we want to construct a polynomial map that is over a small number of variables that contains in its image all non-rigid matrices. And well, there are two parts for the lemma. The first part is to construct a map that has in its image all matrices of low rank. So we would use half the variables to construct a degree 2 map that the image contains all matrices of rank most epsilon n. This is very easy. The second part is to construct a matrix that contains a map that contains all sparse matrices. Here we need to pay a little more in the degree, and then we just take the sum. I guess I should have make it clearer. This is the sum over disjoint variables, right? So Q has I don't know, X, Y, Z, and W as vectors of variables, and then Q1 is over. I'm sorry, Q is over X and Y, and Q1 is over X, and Q2 is over Y, or something like that. So the total number of variables will be 4 epsilon n squared, and clearly, if you can do Q, if we can do Q1 and Q2, we can do all non-rigid matrices because we just plug in the composition of low rank plus sparse. So we just need to explain how we construct Q1 and Q2. Q1, as I said, it's very simple. We want a map that contains all low rank matrices in the image, and we just do it symbolically in some sense, right? So we know that every matrix of rank epsilon n, you can decompose it as a product of n by epsilon n matrix and epsilon n by n matrix. So let's just take symbolic such matrices. One we call U and the other we call V, and multiply them symbolically. So by symbolic, I mean U is just a matrix of variables, and V is a matrix of variables, and Q1 is the matrix multiplication U times V. So this is I have a more explicit way to write this map. The ij's coordinate of this map is this sum, where the entries of U are Uik and the entries of V are Vkj. And this is a degree 2 map, and it's clearly contains in its image all low rank matrices, because again, every low rank matrix you can decompose it, and then you can decompose it as again U0 times V0, and then you set the variables to according to the decomposition, and you get the thing in the image. So this is quite simple, at least I hope. Again, stop me if something is not clear. So this is the low rank part. Now we just need to do part 2. Let's simplify the notation a little bit. We want a map from 2s variables to n squared variables of low degree, where the image contains all s sparse matrices. And it's not as obvious how we're going to do it. But it turns out actually it was already done in a work of Amir Shpilka and Ilya Volkovich in a completely different context. They constructed a pseudo-random generator for read once arithmetic formula, but one of their tools was such a thing. And the construction is, again, it's a bit more complicated than the one earlier, but it's simple enough that I can show you the entire construction. So here's the idea. So let's first pick distinct elements, alpha ij, complex numbers. They can be the integers 1 to n squared. I just for notational convenience, I want to keep labeling them with I and j. But there's really I don't need this thing to be explicit, but I can make it very explicit. So again, I pick n squared distinct complex numbers. And now let's define the Lij to be the corresponding Lagrange interpolation polynomials. By that I mean, once you have n squared distinct numbers, you can find polynomials of degree at most n squared minus 1, which have, they are univariate polynomials, and they have this property that whenever, so Lij has this property that whenever you plug in alpha ij, you get 1. And whenever you plug in any of the other n squared numbers, you get 0. This is just polynomial interpolation. So there are, again, there are n squared numbers and there are n squared polynomials, and they all have this property. If you want to be super explicit, this is the way you define this, or this polynomial. Right? You can just write a simple formula that computes this polynomial. Okay, so now let's define the map, and the map has, again, it's the image is n by n. I can think of, I will just describe what the ij coordinate of the image is. Well, it's this polynomial. Okay, we will do it slowly. From k goes to from 1 to s of this polynomial Lij of xk times yk. So the variables are, maybe I should have written it earlier. The variables are x1 through xs and y1 through ys. These are the 2s variables I promised. And this is what you put in the ij coordinate of the map. And now let's slowly go over it and convince ourselves that this thing contains all S sparse matrices. So how would we do it? So let's assume we want to we want to take the 1, 1 coordinate and to put some element there. We want to show that a matrix that has something in the 1, 1 coordinate is in the image. So the point is that to put something in the 1, 1 coordinate, we can set, for example, x1 to be alpha 1, 1. And what it does is that it makes the coefficient of y1 1 in this coordinate, and the coefficient of y1 will be 0 everywhere else. And then we can just set y1 to be the thing that we want to put in the first coordinate. And then we keep going, right? We still have more variables. Now we want to put thing somewhere in the ij coordinate, or the I prime j prime coordinate. So we just pick x2 to be alpha I prime j prime. And again, this makes the coefficients of y2 1 in this cell and 0 everywhere here. And then we pick y2 to be whatever we want to put in the relevant coordinates, right? Or in total, if we want a matrix that has these elements beta 1 to beta s in those specific indices and 0 everywhere else because it's S sparse, then we just use the x's to pick the coordinates. So for each x, we pick the number alpha that corresponds to the coordinates. And now we have that these matrices would contain the variables y1 through yk. And now we can set y1 through ys. And now we can set yk to beta k, which are the elements we wanted to put in the coordinates. Is it clear? I mean, it's very, there's nothing complicated going on here. I hope it's clear. If it's not, you know, say so. But anyway, the bottom line of all this thing is that this is a map of degree n squared, because these polynomials have degree n squared minus 1, and then you multiply by yk. So it's a map of degree at most n squared. And it contains in its image all matrices which are S sparse. So that proves the theorem, right? I mean, let me go back. We had this two-part plan, and even before that, we said that if we have the lemma, then we have the theorem. So now we have the lemma and we have the theorem. This is, as I said, it's a very simple proof, yeah, I was quite surprised. I mean, I didn't expect this property to hold for sparse matrices, but it turns out that that it's true. All right, time. Okay, good. All right, so this was for rigid matrices. I also promised we can do roughly the same for linear circuits, and the idea is really the same. Again, we find a map that has a small number of variables and low degree, where the image would contain all matrices that can be computed by a small linear circuit. This implied the degree bound in exactly the same manner as previously the theorem followed from the lemma. So how do we do that? Well, this time the map is not that nice to write down. If you have seen related things in similar context of algebraic circuits, then you may have an idea of how to go about. The idea to do those things is always to come up with what is known as a universal circuit. So what you do is that you take the circuit and you sort of massage it to some normal form, and then when you look at the circuit and you just put, instead of coefficients on the edges, you have some symbolic labels on the edges, and this is a way to get a polynomial map that contains all small circuits. This works very well in the case of algebraic circuits as a way to create a universal map that contains in its image all polynomials with small algebraic circuits. But the point is that there you sort of have the game is between polynomial and polynomial circuit size and exponential length of the vector coefficient. So you can allow these massages to the circuits that blow up the size of the circuits. This does blow up the size of the circuit by some polynomial amount, which is, as I write here, it's usually fine, but in this case, the whole game is between n and n squared, and we don't want to increase the circuit size by a polynomial factor, because in this polynomial map, once you reach the number of variables to be more than n squared, it's completely trivial and it won't get you anywhere. So the point is that we nevertheless go ahead and do this polynomial blowup, but then we are able to reduce the number of variables by remembering that even though we didn't blow up the circuit, we still assume that the circuit has at most S edges, or epsilon and squared edges, and we can use this Špilka-Volkovich map to sort of compose it with this generic universal map, and that's how we solve this problem. And as I said, this works for other models, and the idea is exactly the same, even slightly simpler. You can get equations for three-dimensional tensors of small rank or small slice rank, or d-dimensional tensors, and so on. All right, so unless there are any questions, let me describe some. As I said, we don't know if the equations we get, we don't know if there are explicit equations in the sense that they have small circuit complexity. But we do know that it's sort of either answer to this question is good news. What we can prove is the following a bit weird theorem, but still let's state it. So let's suppose for a second that you can do polynomial identity testing. Then, you know, we give two lower bounds and at least one of them is true. One is that there is a hard polynomial family which is computed in p-space. There's just a p-space algorithm that outputs the coefficients of this polynomial family. Or there is an efficient construction of rigid matrices with really, really good parameters with an NP oracle. So the first thing it may remind you is this famous theorem of Cabanets and Impagliazzo that show that if PIT is in P, then again, one of two things holds, two lower bounds result hold. And in their case, these are different things. Another thing it may remind you is a construction of rigid matrices with an NP oracle, which we will hear about in the next talk, I believe, by Ame. So they are, of course, great in the sense that they don't need any of these assumptions or this weird theorem. The only downside is that they don't quite get you the parameters you want for proving circuit lower bounds. So that's the theorem, and you know, you can even strengthen. You can even make the second item to say that you can construct matrices with no small linear circuit, with no linear circuit of size less than epsilon n squared, which is a stronger statement. And you know, how would you know? Well, option one is true if the equations that we found are hard, because then we have a hard polynomial family. And the second option is true if you can do polynomial identity testing in P, which we all believe you can, and the equations are easy to compute. They have a small circuit. You can even do it assuming PIT is in NP. Which is also true for the Cabanets and Impagliazzo result. Here, PIT, it's slightly confusing. I think of PIT as the language of identities. So PIT is in co-NP, even in co-RP, but we don't know if it's in NP. And the proof is, again, pretty easy. The idea is that well, first, the equations are certainly something that you can output in a p-space algorithm, because it's just one way to output an equation is to just solve a linear system of linear equation. It has an exponential size, but it's sort of, you can compute it implicitly, and there are a small space algorithm for linear algebra. We usually scale it down and we say that the determinant is in NC2, which is polylog space, and then when you scale it up, this is what you get. So if this is a family of hard polynomials, that is a family of polynomials that don't have a small arithmetic circuit, then we are done, right? Here's a family of polynomials that you can output in p-space that don't have small circuit. But if they do have, if there is some polynomial upper bound in the circuit, and if you assume that PIT in P, then how would you construct rigid matrix with an NP oracle? The idea is just to guess a circuit and to verify it. Right? We guess some small circuit to the equation. We verify, we assume we have this PIT algorithm, so we can verify that it works. And now you just need to find a matrix M such that P of M is non-zero. This is also something that you can do deterministically if we assume that PIT is in P. So again, if you assume you have this NP oracle, then this is something you can efficiently do. I sort of, yes, there are many details here that I sort of swept under the rugs when you actually come to write down this proof, you realize it's a bit annoying, but this is the basic idea. I mean, if you will read it in the paper, you will have to suffer through annoying details, but basically this is what happens. You just guess a circuit and you verify it, and you find a non-zero of this polynomial, and you know the property of this polynomial that whenever it outputs non-zero, then you know for sure that the matrix is rigid. That's the basic property. So as I said, we don't know if there are explicit equations or not. Actually, let me, this is my first open problem that I want to ask. We don't know if there are explicit equations or not. You may be bothered by the fact that explicit equations give you a certificate for rigidity, which is well, it's easy to give a certificate for, or at least okay, at least over finite fields, it's easy to give a certificate for non-rigidity, and for some parameters, we know that this problem is co-NP hard, so maybe we don't expect a certificate for rigidity in the general case. But the point is that recall that an equation, it's not an if and only if characterization. Equation, the only promise you have is that if it's non-zero, then the matrix is rigid. So the fact that maybe there is an explicit equation, it doesn't say a lot about the computational hardness of the rigidity problem, because it could be that this equation only certifies rigidity for easy instances. Like maybe there are easy instances of this rigidity problem that have a so small certificate. So yeah, I don't really. Of course, the initial intuition is to guess that there are no explicit equations, but who knows, right? I don't really have good reasons to believe one way or another. Of course, we can also not prove lower bounds in general, so it would also be good to rule out existence of explicit equations even under some plausible computational assumption. That would be great to know. But the point is that even if there aren't explicit equations, maybe this degree bound can help giving unconditional construction of rigid matrices. I don't know. I think it's plausible that the answer is yes, but I don't know. One specific way you could try to think of doing it is, and this is something that J.M. Landsberg has suggested to us, is that you can look at very small instances of, I don't know, n equals 4 or 5, and those are rank and sparsity parameters being very small numbers, and you can figure out equations for them, and then maybe you look at them really hard for a few minutes or a few months, and you try to generalize or to make conjectures about general n. And then maybe even you could prove something. I don't know. It sounds like maybe this could work. The only problem is that our results are they are somewhat asymptotic. For this thing to be, we assume that n is large enough, and then of course you get n cubed. When you plug in small numbers, it gives you something, right? Because it was some dimension comparison, and you can pick numbers such that one dimension is bigger than the other for large enough degree. The point is that for very small numbers, this degree d really needs to be large. I don't remember. I did the calculations. It was even for n very small, it was in the order of thousands, I think. And the point is, the computers, of course, can solve linear systems in thousands of variables and find this equation. But it's hard for me to believe that at least I would be able to look at a polynomial in 16 or 25 variables and degree of thousands, and figure out some pattern that I will be able to generalize. So anyway, the point of all this discussion is like maybe there are better ways to do it that you can get reasonable degree bound for small instances, and then look at this equation and try to figure out what's going on. That would be very interesting. And the last open problem I have is to, again, consider this, I call here border rigidity. I didn't use this term before. It's really a way just to consider the variety of non-rigid matrices, in the sense that we look at the closure of non-rigid matrices. And when you look at non-rigid matrices, there's no reason to expect this set to be closed. I mean, maybe it is, and that would be also very interesting, but maybe it's not. And then there are some, there is like a concept of border non-rigidity. And yeah, I don't really have something very concrete to say, except to say that in other areas of complexity theory, like algorithms for matrix multiplication or even VP versus VNP, the problem of proving lower bound for arithmetic circuits, thinking about closure of classes and things like border rank and border circuit complexity turned out to be a very useful notion. We can use it for giving algorithms, for proving theorems. It's just something that's it's a useful concept, and well, as some people say, whether you like it or not, the border is there and it's staring at you, and it's something that we need to understand, and maybe the better we understand it from various point of view, the better understanding we have of rigid matrices. Yes, all right, that concludes what I had to say.
Great. Thank you, Bentley. Any questions for Bentley? We have some time.
Hi. So could you go back to the slide about the consequences if PIT happens to be in P? The one that looks like Cabanech Pagliazzo.
Yes. Don't you hate that when people
yeah, so
go
this
up?
one. So yeah, so here, the first conclusion is something that you could have obtained if you know black box PIT is in P, right? Because there also.
Right. This is even assuming white box.
PIT. Okay, yeah, this is even okay. And like when you say that whatever the equation is either hard or easy, I mean, is one of the things under the rug the fact that it could be easy in the sense that there is a small circuit, but maybe the constants could be large and stuff like that?
Yes, exactly. This is exactly the details I didn't want to give, but
okay.
When you assume it's easy, you need to assume it's actually easy and the constant. So you can think about the constant free model where you only have one as a constant.
Okay. And one other question that I had was this general technique of trying to prove a degree upper bound. Does this work whenever in some sense, the complexity that you're trying to prove, like whatever you consider as low complexity objects, if this parameter is smaller than the number of variables you're working with, does this just work in general? Like in this sense, you're working with a matrix, so there are n squared variables, and you're trying to prove a lower bound that looks like an epsilon n squared sort of thing.
Yes, so it would work in general. I guess the whole point is that in some cases, we take epsilon n squared, and we take epsilon large enough so that the calculation gives that this dimension is bigger than that dimension, even when the degree is small. So as you come closer to n squared, like if you would have a map with n squared minus 1 variables, then you don't expect, right? There are examples for polynomials where the annihilator must have large degree. And you probably know this better than me, but the examples are sort of n plus 1 polynomials in n variables or something like that. Like when you're very close to the threshold, the degree is sometimes big, but the point is in complexity, when you don't care about constant factors and things like that, you can just you can just go small enough for the degree to be really small.
Okay, yeah, thank you.
Any more questions? All right, let's thank Ben Lee again. Thanks, Ben Lee.
Thank you.
So we gained a couple of minutes, but still, we will start at a nice minute, 10:30 India time. We'll start at 10:30 India time for the talk by Ame, 12 minutes from now. Okay, am I ready to start?
Yeah, I'm ready.
Yeah. Okay. All right. Welcome back, everybody. Next talk is by Amey Bhangale. Amey is an assistant professor in the CSC department at University of California, Riverside. Before this, he was a postdoc at the Simons Institute and the Weizmann Institute of Science. Amey obtained his PhD from Rutgers University with Swastik Koparthi as his advisor. Amey works on a variety of areas, including approximation algorithms, PCPs, of course, hardness of approximations, and analysis of Boolean functions. Today, he's going to tell us about constructing rigid matrices using PCPs. Amey, go ahead, please.
Okay. Hi. Yeah. Thanks for the introduction, Satya. In this talk, we'll discuss a connection between PCPs and construction of rigid matrices. So this surprising connection was discovered by Ullman and Chan last year, our first speaker, Josh Ullman. So we will talk about that result, and we'll also discuss a subsequent improvement in the rigidity parameter, which is joint work with Prahlad Harsha or Paradise and Avishekar. So let's get started. Right. So I'll just state. So we all know what a rigid matrix is now that we saw like at least 5 talks. But let me just state the definition. A matrix is rigid, and in this talk we'll just work with Boolean matrices, although the results they hold for even matrices or large finite. So a matrix is called rigid if even after changing some delta entries from the matrix, the rank does not go below rho. Right. So I will use this notation rho and delta. Right. In order to reduce the rank of the matrix to rho or less than rho, you need to change at least delta entries. So this delta is the absolute number, not the fraction. Okay, capital delta. Right, and here is the like an informal picture of easiness and difficulty of constructing rigid matrices. The x-axis is the distance, and the y-axis is the rank parameter. Of course, it's very difficult to construct a matrix such that even after changing, say, many entries, the rank stays very, very high. So that's the upper right corner of the picture. Right. So I'll state just 3 applications of it because the recent construction of rigid matrices, it implies a few of these implications or applications. So this we all know, it implies circuit lower bound because Variant showed that if a matrix A is rigid with certain rigidity parameter, then the function which is you transform x to A times x, it can't be computed by small circuit, right? And in this picture, this x and y axis, the variance parameter is parameters they are at the top. Right here, the important point is that the strict requirement for variance application is that we need the rank to be really high, like almost linear. Okay, but the good part is that the distance is only n to the 1 plus epsilon, that's slightly superlinear. Right. So the second application is in the communication complexity. So if a function f, which is on 2 n-bit inputs, so here the communication model is like this. The function f is known to, there are 2 players, Alice and Bob, and the function f is known to both Alice and Bob. Alice is given the first n bits of the input, Bob is given the second n bits of the input, and they are all powerful. And they want to compute this f of xy. Right, and we only charge for the communication of the bits that they communicate during the run of the protocol. Right, so that's the model. Of course, they can compute this function by sending all the n bits because they're all powerful. So no matter what f is, they can just send all n bits to the other party, compute the function, and then send that bit to the host party. Right, but we are interested in computing functions which can be computed by only polylog n many bits. By just sending polylog in many bits. So so this is the normal P to the CC class which I just described. But then there are variations of it. NP to the CC means that there exists some advice such that after that advice they can communicate and then come up with the function value within polylog n bits. Here you also consider the advice bits in your complexity. right? And PS to the CC is just some natural analog of this NP to the CC, which I just described. Okay, so so Rasborov in '89 showed that if a function is computed by this complexity class PS to the CC, then the matrix MF, which is 2 to the n cross 2 to the n matrix, where the XY entry is the f of XY, this is not rigid. Okay, so in terms of this rigidity parameter, this is epsilon n square versus 2 to the log n to the omega 1. Right? So here I just wrote in terms of this 2 to the n cross 2 to the n matrix, but if you substitute 2 to the n with capital N, then these are the rigidity parameters. So Rasborov showed that if a function is computed by this class PH to the CC, then the matrix is not rigid with respect to these parameters. And in this red diagram, the Rasborov's parameters are is the vertical bar on the right hand side. Right. So here is the opposite extreme compared to the variance parameters. Here the rank parameter is very small, it's very tiny compared to n or log n. But even after changing epsilon fraction of the entries, we need the rank to stay high. So these two parameters are sort of incomparable. Okay, so this is the last application which I'll discuss, which is approximate probabilistic F2 degree. So given a function, you'd like to compute or approximate function by choosing low degree functions from some distribution on low degree function. So there is a distribution on low degree function, okay, that is fixed, and you want to approximate F by just sampling a low degree function from your set and then outputting that value. Okay, so what are the degree bound of the low degree functions? Degree bound on the set. So you have the set of functions, right? And it has some degree bound. And whatever that degree upper bound is, that is the approximate probability of 2 degree. So there is this approximation parameter epsilon, and for every epsilon, you would like to approximate a given function by some distribution on low degree polynomials. And here again, I think so. Here again, we have this implication that if a function f can be epsilon approximated, if the epsilon approximate probabilistic degree of f is small, then the matrix MF is not rigid. I mean, with respect to some parameters, rank and distance. And so we sort of saw a proof of this statement in Josh's talk, right? We talked about low degree polynomials, and we looked at the matrix MF, and we sort of said that, you know, the matrix must not be complex or it must not be rigid. Although there the setting was somewhat different, but morally the proof is the same, right? And what about explicit functions whose approximate degree is large? So we know Rasborov and Smolensky, their result imply that approximating majority requires this probabilistic degree at least square root n. So these are we are talking about functions on n variables. So the maximum it can be is n, and then this result shows that majority requires the degree to be at least square root n. So it cannot be approximated by polynomial of degree less than square root n, literal square root n. Okay, so these are the three applications of you know, why we need rigid matrices. I mean, if why we want explicit construction of rigid matrices. Okay, and then we all talked about this previous construction in the first talk. So a random matrix is highly rigid, linear rank, and constant fraction of the distance, which is constant fraction of the entries. We also saw this the untouched minor argument that for every row, if you consider a matrix where every R cross R submatrix is full rank, then that matrix is rigid with respect to this distance, which is n square or rho roughly. Okay? If you want the rank parameter to be rho, then the distance is n square or rho times log n. So we did see a complete proof of this this second result. Okay, and Ramya also mentioned in our first talk yesterday that if you look at this Topli's matrices, where we only need to know some 2n entries in order to construct the matrix fully, and if you just select a random Topli's matrix, again we are working over F2, so we select some 2n or 2n minus 1 F2 entries uniformly at random, and that gives you a matrix. So Goldreich and Tal in 2015, they showed that this matrix is rigid with respect to this rank and distance parameter. So the third result is stronger with respect to the first result for some ranges of rho. But again, the first construction is in time exponentially in 2 to the n, in time 2 to the n square, deterministic 2 to the n square, because you can just iterate over all the random coins and then come up with a rigid matrix. A second construction is very simple because you just have these explicit matrices, DFT matrix, Cauchy matrices. So that's polynomial time construction. And the third is 2 to the n time construction, because you only need to know some 2n entries to construct the Toplius matrix, or 2n minus 1 entry. Right? So the third one is better than the first one, but the the rigidity parameters are slightly weaker, or a lot weaker than the first one. Okay, and in this talk, I'll talk about these recent constructions. So this is so this surprising connection between PCPs and construction of rigid matrices. It was discovered by Ullman and Chen in 2019, where they gave an algorithm which is a non-deterministic algorithm that runs in polynomial time and constructs a matrix which is rigid, where the distance parameter is the constant fraction of the entries and the rank is 2 to the log n to the 1/4. Okay. Okay, and we'll talk about this result, this particular construction in this talk. And subsequently, we got some improvement in the rank parameters. So we improved that exponent 1/4 to almost 1, in fact better than that. So we got the rank parameter which is 2 to the log n over log n. So this is almost linear. If there is no log n term in the exponent, then this is almost linear rank. Okay, and we use the similar framework developed by Ullman and Chen to come up with this result, but by using some better construction of PCPs, whereas they used off-the-shelf PCPs and tried to construct rigid matrices. And that is the only difference between their result and our result. Okay. So now that we know these two recent constructions, so what do these constructions imply? What kind of implications we have now that we know how to construct somewhat rigider matrices? So the first one is that we know a separation between this class, which is you're allowed to run in 2 to the log n to the omega time with an NP oracle. So, okay, and that class is not contained in this class PH to the C. So there exists a function in this class time 2 to the log n to the omega 1 with an NP oracle, which cannot be computed by this in this communication model, which is PH to the C. Okay, and before this, even E to the NP was not ruled out. So this is a huge improvement over the previous result or the previous separation. Also, they also show E to the NP is not contained in some restricted class of circuit where this AC0 P circuit is a circuit, AC constant depth circuit, where you have access to mod P gates. LTF is a linear threshold function, and so you have these layers of AC0P, LTF layer, AC0P, and then LTF layer. Okay, and then there are some restrictions. Maybe the top fanning is something like 2 to the little low 1. The number of gates in the third layer is there is some bound on the number of gates you're allowed to use in this restricted circuit. But if you have this circuit, then there is a function in E to the NP which cannot be computed by this restricted class of circuit. Again, before this result, we didn't know any such separation. Okay, and because of the improvement in the second construction, now we know that an approximate probabilistic F2 degree lower bound, which is almost linear, but for a function in E to the NP. Before this, we only knew a lower bound of square root n, but that function was in fact in P. Here we go to a slightly higher class, but now we know a much better lower bound, almost optimal lower bound. Okay, so we got this connection by constructing rigider matrices. Okay, so if you recall, I mentioned the connection between the lower bound, the probabilistic degree, and the rigid matrices. And if you just use that statement and the result and this second result, then you get this lower bound of almost linear. Okay, whereas Viola.
There is a question from Arkadev, if you are willing to answer it now, or you could take it later. What does restricted mean on the second bullet?
So restricted means that maybe, so I don't recall the exact restriction, but the restrictions are sort of this. So the number of LTF gates which are in the second layer is 2 to the little o n. You are allowed to use any 2 to the little o n many LTF gates in the second layer. Maybe, and again, the fan-in of AC0P, it might be restricted to square root n. So I'm just making these numbers up. But even after this restriction, this circuit is huge, almost like exponential size. Okay, and okay, so even after this restriction, you have a huge circuit, and then they show that their result implies that this e to the np is not contained in this. So yeah, I don't recall the exact parameters, but again, after this restriction, the circuit is huge.
Okay. Right? Thanks, Amay. Continue.
Okay. Right. And the second result, the advantage of second result is that this connection between PCPs and matrix rigidity or construction of rigid matrices, it is simpler. Although one might argue that the actual construction of the PCPs that we need for this implication, PCPs to rigid matrix construction of rigid matrix, that might be complicated. But once we have the PCP theorem as a black box, which we'll talk about next, then this connection between PCPs and rigid matrix is quite simpler than Holman and Chum. And even this construction, it says that the rigidity parameter, they are tied with respect to the PCP parameters. And I'll also just mention a few lines about this, the last comment. Okay, but in this picture, we met this Rasbourg's bound, in fact, much better than Rasbourg's bound. And that's why we have the first implication. The Ullmann-Chen result, it has this first implication. Whereas, yeah, the variance regime, we don't know how to construct matrices in that regime. Okay, makes sense? So let me start defining, if you don't have any questions, so let me start defining what are PCPs, and then we'll go and see how we construct rigid matrices from PCP. Okay. So suppose we want to prove a mathematical statement, and as a complexity theorist, you can just think of a statement as some three-side instance being satisfiable. So given a three-side instance on n variables with, say, maybe order n clauses, you want to decide whether this is satisfiable or not. It's a mathematical statement. Okay, and as a verifier, you would like someone to give you a proof that this three-side instance is satisfiable. Right. So there's a very easy way to convince a verifier that if the three-side instance is satisfiable, then there's a very easy way to convince the verifier. Right. You just write down the assignment, like all the n bits, and assignment, satisfying assignment, and the verifier can just go over all the clauses and make sure that every clause is satisfied by the given assignment. Right. Right, so this is a standard way of verification. Just write down the proof and then run in polynomial time and check whether the proof is correct or not. Okay, and PCP is similar, except that so the PCPs is a special type of proof where you can convince, the verifier can convince itself that the proof is correct or not by just reading a few locations in the proof, as small as, say, 3 locations in the proof or 10 locations in the proof. Although the proof is of size n, which is growing, the PCP is it provides a way to write down a proof in a specific format, so that now the verification procedure is very easy. Okay, so there are 2 differences. One is that the verifier needs random points. Okay? It's not a deterministic verifier. No. Okay? So it tosses some random points. It decides a few locations in the proof to look at. It gets the proof. It gets the information in these proof locations. And then based on it, the verifier decides whether to accept or not. Accept meaning that the proof is correct, the mathematical statement is correct, so I'm convinced that the proof is correct, and reject means that I'm not convinced if the proof is correct. Right? Any questions? If you're seeing PCPs for the first time, then let me know if you have any questions. Okay, but the picture is like this. The verifier has access to randomness. It has access to the input, which is the three-side instance or the mathematical statement. And now the prover can write down the proof so that it is much easier for the verifier to get convinced that if the proof is correct or not. Okay, and of course, this is a proof system, right? And we need two important properties from this proof system. One is the completeness, which is every correct claim can always be proven. So if the statement is correct, then there is a way to write down a proof, okay, such that the verifier accepts with very high probability. Think of C as very close to 1. The completeness is very close to 1. Right? So this is a natural thing to expect from any proof system. And even the second thing is natural to expect from any proof system, which is that if the claim is incorrect, okay, so then there's no way to convince verifier with high probability that the proof is correct. So it means that no matter which proof the prover comes up with, when the verifier runs its decision-making thing on this proof, the verifier accepts with very small probability. Okay, so C is very close to 1. Think of C being very close to 1, and think of S being very close to 0. Okay, so for every correct claim, there exists a proof, so that the verifier accepts the proof with high probability. So this probability is over the randomness R that the verifier is using. Okay, and in the soundness, if it is incorrect, false, then no matter which proof the prover provides, the verifier accepts the proof with very, very small probability. And this is the main completeness and soundness guarantees of a proof system. Okay, and there are other important parameters, so, and which will be crucial for our application of constructing rigid matrices. One is the size of proof. So if you think about the mathematical statement as 3 SAT, then the trivial proof is just a set of n bits, which is the satisfying assignment, right? And so we compare the size of the proof with the actual witness. So how large is this proof size compared to this size n, which was the usual witness size, right? So it will be crucial that the PCP system that we'll be using, the proof size is always comparable or almost similar to the actual witness size. And then second is the number of queries, how many locations the verifier is going to probe from the proof for every random coin. The gap between the completeness and soundness, right? In the completeness, we want the verifier to accept with very, very high probability, almost close to 1. And in the soundness, we want the verifier to accept with extremely small probability, very close to 1. So the gap between the C and S, it is important. The fourth parameter is the verifier running time, right? The verifier has access to this 3 SAT instance. It gets these random coins. And based on both these things, it decides which locations to probe. Right, so this particular mapping from this PR to the locations that should be efficient. Okay? And this will be crucial for our application too. But this is what I mean by the verifier's running time. The time the verifier needs to calculate the query locations based on the randomness. And the fifth property is the smoothness property. We want a PCP system where every proof location is queried equally often. Okay, so we don't want a PCP proof where maybe these locations are queried by 99% of the random coins, and maybe these locations are queried by only 1% of the random coins. Okay, so this is like non-smooth PCP, and smooth is the opposite, which means that every location, if you look at the marginal probability that the verifier is querying this particular location, this should be the same for every location. Okay, and this is the notion of smoothness. Okay, any questions about this PCP parameters? Okay. Right.
Yeah.
Any question?
Oh no, it doesn't look like there is any. Go ahead, please.
Okay. So we know how to construct extremely efficient PCPs for this for any language in n time t of n. Okay, so n is the input size, and t of n is the witness size. For this is the class n time t of n. For any language in this class, we know extremely efficient PCPs. What do I mean by that? The size of the proof is extremely close to the witness size. Right? So the witness size is t, and the size of this proof is t times polylog t. Up to this log t factor is almost the witness size. The number of queries, the verifier only queries some constantly many locations from the proof. Okay. And the gap between completeness and soundness, you can make it as small as possible. So the completeness is 1, which is as good as you can hope for. means the correct proof is always accepted, no matter which random points the verifier is tossing. And any incorrect proof or incorrect statement, it is accepted with priority epsilon. So you can make this epsilon as small constant as possible by increasing the number of queries to some bigger constant. Okay. And the verifier running time is also extremely efficient, is poly in log t. Also this PCP can be made smooth. So all the locations are equally likely to be queried. Okay, and now here is the main technique in or the main argument that which shows the connections between PCPs and rigid matrices. Okay, so this slide, we'll see this slide many times. So this slide will be crucial for the rest of the talk or some additions to it. Okay, so let me know if you have any questions once I describe this construction. Okay, so the starting point is you fix any unary language L which is in this class n times 2 to the n, but not in this class n times 2 to the n over n. Right? By the non-deterministic time hierarchy theorem and a result by Zach, we know such a unary language always exists. So you fix any such language which is in n times 2 to the n, but not in n times something which is smaller than 2 to the n. Okay, and then given an input x in input x, right, which is 1 to the n, unary input x. So let pi be the proof in this PCP system, the PCP proof that x belongs to the language. Okay, of course we are talking about proof, and we were just writing proof as a string, and you can just think of a proof as a matrix. Just arrange the proof arbitrarily in a matrix form. Okay, and that's what I mean by look at a proof in a matrix form. Right? So it's not, for now, as of now, it's not important how you arrange the proof entries, but just arrange arbitrarily into a matrix. Now the claim is that this matrix cannot be delta approximated. So delta is the fractional Hamming distance now, the small delta. The claim is that delta cannot be, pi, the proof cannot be delta approximated by a low rank matrix. Okay, so this is what we are going to show. Okay, and why not? Because if it were, then we'll put L in this smaller class, which is a contradiction, right? Because L was in this class, but not in this class. And if this statement is true, that if every proof can be delta approximated by a low rank matrix, then we'll do some more things, and we'll show that this language L, in fact, we can put this language in a smaller complexity class, and which will be a contradiction. Okay, so let's see. So suppose this is not true. What does it mean? That there are two matrices A and B. Okay, so that A times B is very close to pi, right? Because we are assuming that the proof pi written in a matrix form can be delta approximated by a low rank matrix. So let A and B be the low rank decomposition of the low rank matrix, right? And again, since we are talking about the proof system which was very efficient, so the original proof size was roughly the witness size times polylog witness size, which is 2 to the n times polylog n. The size of A and B collectively is much smaller than 2 to the n over n. Okay, we are thinking of rank which is smaller than 2 to the n over 2, much smaller than 2 to the n over 2. Right? So since the proof is almost of size 2 to the n, the size of A and B, and we are approximating this matrix by one tall and one fat matrix, very tall and very fat matrix. The size of A and B collectively, it is much smaller than 2 to the n over n. Of course, by setting this rank parameter appropriately. Right? Okay. So, okay, and then we would like to simulate the verifier on this product matrix A times B. Right? A times B is a matrix, okay, which is delta close to pi. That was our assumption, right? And now we would like to, so we would guess A and B, which is, so in this guessing part, we are spending much smaller than 2 to the n over n non-deterministic time. Okay, so that is allowed. So this blue region, we are trying to put this L in this complexity class n times 2 to the n over n. Right? So we guess this low rank decomposition A times B, and we would like to simulate the verifier on this product A times B. Okay, and simulate meaning that, you know, go over all the random coins, look at how many fraction of random coins the verifier is outputting accept, and on how many random coins the verifier is outputting reject. Calculate that fraction, and then if that fraction is very close to 1, then we know that the x belongs to the language. And if that fraction of accepts is much smaller than the soundness parameter, then we know that the x is not in the language, right? So we would like to simulate this verifier on A times B, and here we use the smoothness parameter of the PCP system, right? So what we know is that pi star, the correct proof if x is in the language, it is very close to this product A times B, right? And the verifier is issuing Q queries, and each location is equally likely to be queried. So even after this delta fraction of the error, if the original acceptance probability is 1 on pi star, the acceptance probability on A times B would be 1 minus Q times delta. This is just by union bound. Right? And again, think of delta is very small compared to 1 over Q, so this is very close to 1. And the soundness, no matter which proof you provide, this number will always be very close to 0. So these two, there is a gap between these two numbers, and if you can calculate this acceptance probability efficiently, then okay, if all this verification is done in time 2 to the n over n, then there's a contradiction. Okay, and that's how yeah. So that's why this claim is true, that pi cannot be delta approximated by low rank matrix. Of course, I need to show you how this can be done. All the verification is done in time 2 to the n over n. But this is the high level overview of the initial step of the construction. Right. So from this, how do we get rigid matrices in non-deterministic time? Okay, so okay, what is the implication of this? Since this is a contradiction, so this must fail for infinitely many n. So for many inputs, if that input is in the language, then the proof cannot be delta approximated by low rank matrix, and this is the notion of rigidity that we are after. Right, so which means that this proof must be rigid for infinitely many n, because if not, we are going to put this language in a class which is smaller than 2 to the n, and that's a contradiction. Okay, and this gives rise to this non-deterministic time machine outputting rigid matrix. So what is it? So on input 1 to the n, the machine does the following. Let L be the language from the previous slide. The input to be 1 to the n, where this capital N is 2 to the n. Okay, and then you guess the proof pi of the statement. Okay, so you're allowed to run in poly times capital N time now, because this is the machine that outputs a rigid matrix on input 1 to the n. So you're allowed to run in time poly times capital N. Okay, so you guess the proof pi and then output this matrix pi. Okay, again, the proof pi is of roughly size 2 to the n. That's why the matrix is of dimension n over, like 2 to the n over 2 times 2 to the n over 2. I think this should be 2 to the n over 2. Right, and by the previous claim, for infinitely many n, this matrix pi must be rigid. Right, and this is the main construction, and this is the main construction of for constructing rigid matrices from PCP. Okay, again, on this input, you just consider a smaller input x, which is 1 to the little n. Then you guess the proof that x is in the language. If x is not in the language, then you just output anything. But if x is in the language, then you guess the PCP proof, the pi star. Okay, and then you output that matrix. And by the previous claim, for infinitely many n, this pi star must be non-rigid, because otherwise we are going. This previous thing showed that otherwise we would put this language in a smaller complexity class, which will be a contradiction. So does this make sense? Okay, so all I need to show is that, of course, you are allowed to guess this low rank decomposition, because the size of A and B, number of bits in A and B, it is much smaller than 2 to the n over n. So you are allowed to guess this thing, but you are not allowed to multiply A and B, because if you multiply A and B, there will be 2 to the n times poly n entries, but we'd like to simulate everything needs to be done in time less than 2 to the n over n. So you're not allowed to multiply these matrices and run the verifier on it. Okay, so somehow we would like to keep the matrices A and B as it is and run the verifier or simulate the verifier on this product A times B without calculating the product. Okay, and this needs to be done in time less than 2 to the n over n. Okay, and what do we mean by simulation? Just need to calculate the acceptance probability in time less than 2 to the n over n. Okay, and then if you do this and this, then all the verification can be done in time less than 2 to the n over n, and that will be a contradiction. Okay, again, I mean, when finishing this argument, this was a big if statement, right? And we are going to see how this can be done in small amount of time. Which is counting number of ones, which is counting the number of ones in a product of two low rank matrices. Sorry, I think my internet is unstable. Is it better now, the internet?
There was about a 5-second or 5-second-ish period when we couldn't hear you.
Okay, so now,
yeah, it's better.
It seems fine. Yeah.
Just to repeat, sorry.
Yeah. No, go ahead.
Okay, just to repeat what I said in the last 15 seconds. Now we need to show that how do you simulate this verifier on this product A times B without actually calculating the product A times B in time less than 2 to the n over n, right? And in calculating this acceptance probability, we are going to use this faster algorithm for counting number of ones in low rank matrices. Again, this is I mean, this way of calculating the acceptance probability was used in Ullman and Chen. And in the second result, which is this joint work with Harsha, Orr, and Tal, what we did is that we used some other PCP, which we call rectangular PCPs, and using that, all the simulation can be made extremely simpler. Okay, and that's what we are going to see. But the overall approach was similar to this Ullman-Chen result. Okay. So this is the rest. I'm going to discuss in the rest of the talk. I will introduce rectangular PCPs. Okay. Now we know what PCPs are, right? I'll introduce this rectangular PCPs, and I'll convince you that the simulation can be done in time 2 to the n over n, non-deterministic time, right? Because that was needed for the argument to finish. And in this process, I will also mention where are we using this fast counting algorithm, the counting number of ones in a product of two low rank matrices. So, so these are the three important points that I'm going to cover in the rest of the talk. Okay, so again, PCPs, the way I defined it, it's a proof written in a string format. The verifier processes random coins, probes locations, and then accepts and rejects. And one important property, one important thing in the usual PCP without any restriction is that for every query location, each query location might depend on all the randomness and this input. Okay, so I never said, okay, what part of randomness is used to query the first location and so on. So this Q1, the location of the first query, once the random coins are tossed, the location of the first query might depend on all the randomness. Okay. And this will be crucial in defining rectangular PCPs. Okay. So there are two changes that we do in this rectangular PCPs. One is that we'll always think of a proof as a matrix. Okay, so just write down your proof in some square matrix. Okay. Now every proof location is defined by the row index and the column index. Right? No matter which proof location you take, it is defined by the row index and the column index. Right? And the important distinction on how you are going to query a proof location based on randomness is that for every query, say the first query, the verifier wants to get this query. The important point is that the row index of this query is determined by some, say, half of the randomness, and the column index is determined by the second half of the randomness. Okay, and so this is the only restriction we are going to put on this verifier. Okay, so there is this randomness R. We are going to split the randomness into two halves, R row and R column. These are just some random bits. And in order to probe the first location, the row index of the location is determined by the first half of the randomness, and the column index of the location is determined by the second half of the randomness. And same is true for every location. Right? And this is what we call rectangular PCPs. Okay, so this is just some restricted way of accessing proof or the locations or coming up with the locations based on the randomness. So so this is the only difference between PCPs and rectangular PCPs. And of course, we are thinking of proof as a matrix now because we are talking about row index and column index. Okay. So perfect rectangular PCPs are not possible. You can show but we'll talk about almost rectangular PCPs. So the only difference is that instead of splitting the randomness, partitioning the randomness into two halves, we have some shared part, which is some small fraction of the random bits. Okay. And now the only change from the previous slide is that the row index depends on R row and R shared. So the shared part, you are allowed to use the shared part in coming up with the row index as well as the column index. Okay, that's why it is called a shared part. Okay, so the row index depends on R row R shared, and the column index depends on R column R shared. And think of R shared as a very small fraction of the overall randomness. Tau is like 0.001, and R row and R column are like two equal sized partition of the rest of the randomness. Okay, and this is what we call tau rectangular PCP. Okay, and the main theorem which we showed is that like the PCP theorem that I stated earlier, that now we also know how to construct rectangular PCPs with extremely good parameters. Okay, so the main theorem is that for every language in n time 2 to the n, you can replace this 2 to the n with any t of n, but I'm just stating it for simplicity. Right. So there exist PCPs where the completeness is 1, soundness you can make as small as possible, maybe at the expense of increasing the query, but still constant. So the query complexity is constant. The proof size is extremely small, like witness is of size 2 to the n, so the proof size is almost linear in 2 to the n. Even this also means that the randomness complexity is like almost n plus order log n. The verifier running time is not poly log n, but it's better than just exponential running time. Okay. So the verifier's runtime is 2 to the epsilon n, where you can make epsilon as small constant as possible. Recall in the earlier PCP theorem that I stated, the verifier's running time was poly n. It has some drawback of exponential running time, but we can use this PCP, but it won't hurt our construction, which we'll see. So there is a question by Kadir. Was the notion of rectangular PCPs existing before this work? No, it was not. No. Yeah. So the thing is that we looked at the proof of Ullmann and Chen, and then we thought that okay, this way of accessing the proof might lead to efficient, like even better parameters, and that's how we came to this. But yeah, as far as I know, this was not known. Okay, and again, the PCP is smooth and it is tau rectangular, and again you can make this tau as small as possible. Okay, and now again, I need to tell you how to simulate the verifier on A times B. You guess these two matrices A and B, which are close to the actual proof pi star or pi, right? And now I need to simulate the verifier on this matrix A times B in time much smaller than 2 to the n. Okay, so what is this A times B? So again we assume that the matrix proof matrix pi is approximated by low rank matrices A and B. Right, so that's why it's a very tall matrix and very fat matrix A and B. If you multiply A and B, you get a proof pi, and all you need to do is go over all the random coins, look at the proof locations, and then run the verifier on every random coin, and then decide on how many fraction of random coins the verifier is accepting, and on how many fraction of random coins the verifier is rejecting. Right, and once we know the exact value of this, we'll be done. We can decide the language like with probability 1, we can decide the language in time less than 2 to the n or n. Right, and that will put this language in this class. Okay, and for simplicity, we are going to assume that the verifier's predicate is just it queries 3 locations and then it takes the parity. If it is 1, then it accepts. If it is 0, then it rejects. Okay, and this is just for simplicity for the talk. If the predicate is, just to state, if the predicate is somewhat complicated predicate based on 100 locations or 100 bits, you can use Fourier expansion of it, and all you need to do is just calculate parities on the argument I'm going to present here to compute the parity. It's, you're going to use the same argument to compute each parity in the Fourier expansion, and then you can combine it to get the actual predicate value. Okay, but for simplicity, the verifier is extremely simple. It tosses random points. It probes this location Q1, Q2, Q3 in a rectangular fashion, which I described earlier. And it takes the parity of these 3 bits. If it is 1, then it accepts. If it is 0, then it rejects. Okay. So from A and B, I'm going to construct 3 matrices. From A, I'm going to construct 3 matrices A1, A2, A3, and B1. From B, I'm going to construct 3 matrices B1, B2, B3. First, okay, before that, I'm fixing a shared randomness Z. Okay, and condition on this shared randomness, I'll calculate the acceptance probability, and then I'm going to enumerate over all the shared randomness. Okay, so that is the final goal. So fix a shared randomness. Now all we need to do is calculate the acceptance probability condition on this shared randomness being Z. Okay, and for that I'm going to do this particular procedure. Okay, so from A, I'm going to construct a matrix A1, A2, and A3. From B, I'm going to construct matrices B1, B2, and B3. All these matrices are indexed by R row, right? So what are the size of R row? 2 to the size of that R row. These are the number of rows in this matrix AI. And similarly, these are indexed by the bits R column. Okay, and the ith row of A1, fix A1. So ith row of A1 is the row index of the first query in the proof. Recall, these are indexed by R row, right? So I can talk about the row index and Z. This collectively determines the row. So I can talk about the row randomness and Z, right? And this row randomness and Z, this is the row randomness and Z. This defines the row index of the first query, right? That was the definition of rectangular PCP. And on this ith location, I'm going to put that particular row of the matrix A. Okay, so again, we only had these 2 matrices A and B. From this, I'm constructing A1, where on the ith row, I'm going to put some row of A, which is basically the row which is queried by the verifier on randomness I and Z. Right? Because Z is the shared randomness, and we are indexing the row by the row randomness. So row randomness and Z gives you the row index, and I'm going to put that row of A in A1. I do the same thing for the second query. I'm going to put the row given the row randomness and the shared randomness, what are the row the verifier is probing, I'm going to put that row in this row J, row I of this matrix. And I'm going to do the same thing for these matrices B1. The same thing for the column. Right. So since there are 3 queries, I have these 3 matrices A1, A2, A3, and B1, B2, B3. These are just some reshuffling of the rows of A. Each matrix AI is a reshuffling of the matrix A. Each matrix BI is the reshuffling of columns of the matrix B. Okay, and the reshuffling is based on this particular. Okay. Now, if you look at so ijth entry of this matrix. Okay, again, I is R row, J is some R column, and you fix the shared randomness. So the ijth entry is the parity of 3 bits queried by the verifier on randomness, on the full randomness I, R shared, and J, where R shared is C. Right, and this is just because the way we are setting up the ith row of this and the jth column of B. Right, so the ith row of this is the row queried by the verifier, or the row index queried by the verifier on this randomness. Similarly, this was the column queried by the verifier on the randomness J and Z. So if you multiply these two, you get a parity. You get the first bit location, queried by the, or the first bit queried by the verifier. If you multiply this row and this column, you get the second bit that the verifier queries. If you multiply this row and this column, you get the third bit. And since this is a matrix multiplication over F2, ijth entry is precisely the predicate value. We are assuming the predicate is just parity on 3 bits. Right? So ijth entry is precisely the 1 or 0, 1 when the verifier accepts on this randomness R row, R column, and Z, and 0 if the verifier rejects. Right? Any questions so far? Okay. And now I'm going to tell you how to do the overall simulation. Again, we are going to fix the shared randomness. We are going to enumerate over all the shared randomness. And now all we need to do, so again, I defined this matrix MZ for the shared randomness Z. It is just 0 and 1 matrix. Right? So I'm going to calculate the fraction of ones in this matrix MZ and let that fraction be PZ. And now the acceptance probability of the proof A times B is expected value of this PZ. Right? Because for a fixed shared randomness, you calculate what is the acceptance probability. And now you need to average it out for all the shared randomness. Right? So the overall acceptance probability of the proof A times B is nothing but this expected value of PZ. Right? And whereas PZ is the fraction of ones in MZ. Right? So this is how we are going to calculate the acceptance probability on the proof A times B. Okay. And we need to see now that this can be done in time less than 2 to the n/n. And this is mentioned here, but does this, I mean, is it clear that this will give us the acceptance probability of the verifier on the proof A times B without actually calculating the proof A times B? Okay, I need to show again. I need to show how to calculate PZ, but once that is there, everything you can calculate the acceptance probability. Okay, so let's calculate the running time. So we are iterating over all the shared randomness. So that's 2 to the tau times n, because the shared randomness is of size. Again, I'm assuming the randomness is n, whereas it's n plus log n. But for simplicity, I'm just assuming the randomness to be n. The shared randomness is right. It has tau times n bits, so we are iterating over all the shared randomness. And then we are setting up these matrices A1, A2, A3, B1, B2, B3 from A and B. A and B we have guessed using non-determinism. Okay, and so these are matrices with these many entries, 6 times. These are the number of rows of A or columns of B. These are the number of columns in A and rows in B, because we are assuming the rank of A was row, rank of the matrix pi was row. And there are 6 such matrices, right? So these are all the entries in the matrices A1, A2, A3, and B1, B2, B3. And here we are using the verifier's running time, right? From the randomness to the row location, the verifier is spending 2 to the epsilon n time. Right? Looks at the random bit, it spends 2 to the epsilon n time, and then decides which row location to probe. Right? So in order to set up these matrices, you need to spend, for each row, you need to spend 2 to the epsilon n time. Okay, so all this, you can set up all these matrices in time. These are just the entries of the matrix, and this is just the verifier running time to map our row R share to the row index of the query location. Okay, and now all we need to do is how much time are we spending in calculating the quantity PZ. Again, PZ is just the number of ones in a product of 2 low rank matrices. Right, and here we use the main algorithmic tool or faster algorithm to count number of ones in a product of 2 low rank matrices. So this is precisely the PZ. Okay, and here we are going to use this result by Chan and Williams, and it was also in Allman and Chen, a slight variation of result by Chan and Williams, that given 2 low rank matrices, so these are n cross R and R cross n. We would like to compute number of ones in this product X and Y. They show that this can be done in roughly time slightly smaller than n square. So n to the 2 minus 1 over log R, where rank is, if rank is n to the little o 1, this can be done in subquadratic time. Right? Whereas if you want to multiply these matrices, the trivial way is to multiply these matrices and then count the number of ones. But that takes at least n square times row time, n square times R. Right? Whereas this algorithm is much more efficient than the trivial way of counting number of ones. Okay, and if you look at our matrices, its dimension is 1 minus tau n over 2, because that's the size of the row randomness. right? So n square would give you this factor. And then this is the crucial saving in the algorithm which appears here. Okay. Because the right, based on since our matrices is of rank row, this saving gives you this factor here. Okay, and now if you multiply all these numbers and set a row to be roughly 2 to the n over log n, you get the total running time of the simulation is smaller than 2 to the n over n. Again, this factor savings in the running time compared to this 2 to the n is coming from this here. Where you multiply where you count the number of ones in a multiplication of two low rank matrices. And this saving appears here, and this is the crucial saving in the simulation. Okay, and this shows how to do this simulation in time less than 2 to the n over n. Okay, and now we are done with the proof. Right? So, right, and right, and so this finishes the proof. Again, so we started with a language in this class n time 2 to the n, which is not in this class n time 2 to the n over n. And it must be the case that for infinitely many inputs x in the language, the proof pi star must be rigid. Because if not, we showed how to simulate the verifier on the low rank decomposition of the proof, which is close to the proof, in time less than 2 to the n over n. Right? So it must be the case that for infinitely many n's or inputs, the proof, the PCP proof, must be rigid. Okay, and that gave us the non-deterministic polynomial time algorithm to construct rigid matrices. Okay, and that's the end of the proof. So let me just finish by a couple of questions. If you look at the faster matrix the counting number of ones in a product of two low rank matrices, it only works for rank which is n to the little o1. Okay, whereas I mean you can go up to rank maybe n to the 1 minus epsilon. Right? Even if you have like n cross n to the 1 minus epsilon and n to the 1 minus epsilon cross n matrices, compute the number of ones in the product. Okay, does there exist a faster algorithm for counting number of ones for higher rank? And if you come up with this, then this will imply better rigidity parameters, because as I said, this particular construction is tight with respect to PCP parameters. So even if you improve PCP parameters, the proof length from 2 to the n poly n to 2 to the n times log n maybe, it won't give us significant improvement in the rigidity parameters. But if you improve this fast counting algorithm for higher rank, then it will imply much better rigidity parameters. Okay, and again, so the algorithm of Chan and Williams, it's a deterministic time algorithm, and it computes the number of ones exactly. Whereas for our application of constructing rigid matrices, we are allowed to use non-determinism, and we are also allowed to make some error because there is a gap between this completeness and soundness parameter, right? So in the yes case, there are like 99 fraction of ones. In the no case, there are only 1% of 1% of ones in the matrix, right? So we are allowed to make some error. Even if your output is 30% correct, like up to 0.3 here and there, that's okay, or 0.2 here and there, that's okay. And we are even allowed to use non-determinism. Okay, so now the question is, even with this, can we come up with a faster algorithm for higher rank? Okay? And if we can do that, then it will imply better, like rigider matrices. Another question is, this framework of using PCPs to construct rigid matrices, can it be used to construct other complex objects? For example, the question which I asked yesterday was this rectangular rigidity, right? Where you only count the changes that you do in rows compared to the average changes in this approximation by low rank matrices. Okay, and maybe because of the structured way of perturbing the matrix, can it give us more freedom to go beyond these parameters for matrix rigidity? Can we get better rectangular rigidity parameters using the same framework and the same algorithm? So that is also a good open question. Yeah, that's all I have to say. And thank you for listening.
Thank you, Amey. So we have time for questions. Any questions to Amey?
Hi, Amey. This is Arkadev.
Mm-hmm.
So two questions. First is, so this Ullmann-Chen did not use the notion of rectangular PCPs, right?
No, they did not.
This was, I mean, so I didn't. I think I lost somewhere because I thought that rectangular notion was crucially used to get the simulation time under 2 to the n by n, right?
It's not crucially used. It's crucially used to, for this image, how to compute this this acceptance probability in a simpler way. Whereas Ullmann and Chen,
Amey, I think we
can't hear
lost the audio from you. Yeah. Amey, can you hear us?
talking about proof as a matrix. Sorry.
Hey, Amey, I think we lost the audio from you. So could you go from the beginning? Could you start
So I'll repeat
the response from the beginning?
Right. So I'll repeat my answer. So the question was, how did Ullmann and Chen did this simulation in time less than 2 to n, or whether we did that? And the answer is yes, they also did the simulation in time less than 2 to n or n, but using usual PCPs and some PCP composition. Okay, and for that they had to go in a roundabout way to calculate this acceptance probability. Okay, and in our paper, once we introduce these rectangular PCPs, to calculate the acceptance probabilities on this rectangular PCPs, it is much simpler. So again, both are doing the simulation in time less than 2 to the n or n. Using rectangular PCP, this argument is much simpler than Ullmann and Chen. Does that answer your question?
Yeah, that was the first question. Thank you. Second is, so what is now the best known lower bound for LTF of LTF?
Yeah, so I might not be able to answer that question, but
I mean, Josh is around, so Josh, if you can,
well,
pitch in.
If he's awake, it's pretty late for him. So I don't know.
Oh, I see. Okay, yeah.
I am
yeah,
kind of here, but a little bit tired.
Okay.
I
Josh,
don't.
if you
Yeah, I don't.
Go ahead. Sorry.
I don't remember off the top of my head. I'd have to look into it. I don't think this this rigidity approach gives the best lower bounds for just LTF of left LTF though. I think like maybe a past paper by Ryan and Daniel Kane is currently the best. But I don't remember off the top of my head exactly what it is though.
I think that lower bound is n to the 3/2, if I remember correctly.
Right, that is true. That's just n to the 3/2.
Right. But I was not sure whether the circuit was LTF or LTF. So,
but for this one, you're saying, didn't you say that you get exponential lower bound or super polynomial lower bounds?
No, but you have some restrictions. Again, I'm not aware of the precise restrictions, but there are some restrictions.
No, but I'm just talking about LTF of LTF. You had a more complicated circuit, right? I'm just talking about depth to threshold circuits.
So maybe Josh?
Yeah, I think the issue is that for the middle layer of LTFs, in this proof there's an upper bound on what the fan-in of those gates is allowed to be.
Oh, I see.
I think if you get rid of the AC0 in the middle, it makes it not a very interesting result anymore.
Right. Because the reason I'm saying that is because it's not known whether just matrix rigidity is enough to give you lower bounds for depth to threshold, right?
I see.
Isn't that right?
I think that's. Yeah, I think that is right.
Okay. Thanks.
Yeah, we currently don't know how to do that.
Yeah.
Okay. Any other question?
I don't see anything on the chat either.
Okay.
Any questions from anybody before we wrap up?
Oh, one other question. Sorry.
Yeah. Okay. So, Arkadev, go ahead.
So for this rectangular PCPs, so you, I mean, I think you didn't have time to tell us about how to construct rectangular PCPs, right?
Yes.
So is this very different or some, I mean, you require new ideas to construct them?
No, so we just took the original construction of this BGHSV PCPs that I mentioned earlier, right? The PCPs with extremely good parameters.
Right.
We went over that construction, looked at the the mappings from randomness to query locations, and then made sure that this can be done in a rectangular way, right? But that was not just an observation, because maybe that is very easy to observe that it can be done in a rectangular way. But then the problem was that the PCP was not smooth. And then for that, we need to work somewhat harder so that the final PCP is smooth. But just getting rectangularity is not very difficult. It's very easy to observe from the BGHSV proof, the PCP proof, or the query, the randomness to query map. That's what it's also.
Okay, so you're saying, so usually the smoothness property, so I guess again, Ullman and Chen also required the smoothness property, right? Of
Yes,
PCPs.
yes.
Yeah, sorry for my ignorance
Right,
of PCPs,
yes.
but so I guess the smoothness property is something that's there in usual PCPs, but when you combine it with rectangular PCPs, then you have to do something non-standard. Is that right?
Right. So smoothness is very easy to get from any PCP which is non-smooth. So you can convert any non-smooth PCP to smooth PCP a little bit. So very easy. But then it's not clear whether how it maintains the rectangularity, right? So because of this reason, we had to carry over some more information from the original proof, the outer PCP, so that we can do this procedure without hurting the rectangularity.
Okay, thanks.
All right, so let's wrap up then. Thank you very much, Amey. Thanks for the fantastic talk. And thank you all the speakers in this session, Josh, Ben Lee, and Amey. And also, thank you very much all the organizers for organizing this workshop as part of FSTTCS. Thank you, Amey, of course, is one of the organizers. Amit, Ben, Sasha, and Mrunal. Well, so Amit, do you have anything to talk about the workshop or anything administrative stuff? So I guess we could close after your closing remarks.
I think the gather town is
your audio is breaking.
Are we having gather town now? Is that what Mrinal is trying to say?
Oh, yeah. Sorry. Hi, Meena. I wasn't trying to say anything. I think Amey was trying to say something about gather town. Also, from the from the side of the organizers, yeah, it was great to have people attend the workshop and so on. So thanks to everybody in the audience. And yeah, hopefully, yeah, it would have been nice to have this workshop, physically during normal times and so on. But yeah, such is life at this point. So yeah, yeah, thanks so much, Meena and Satya, for agreeing to chair the sessions on both the days. Amey, you heard an update about Gather Town?
Yeah, so maybe I need to check, but if the gather town is available, please feel free to go there and talk to people. And you can always use the Slack channel if you want to go over the talks again. And if you have some questions, please do ask the questions on the Slack channel. We'll make sure that we answer your in time.
So would the slides be available?
Yeah, we will try to get the slides available on the workshop webpage maybe in a couple of days.
Right.
Thanks.
Okay, I guess so. That's all from my side, and hope to see you all in the actual conference and maybe other workshops.